Yeah, thank you very much for the very kind invitation and introduction. And I'm honored to be called a specialist on the topic of compact stars. Actually, it's difficult to be a specialist on compact stars because we don't know much about these guys. The good thing is we know more about them than we knew 3 years ago, but still this is really research in progress and lots of things can be learned and need to be understood. Yeah, the topic, if I speak too fast, raise your hand and I will slow down. And if I speak too slow, do the same. So you can adjust my person to your needs. And of course I encourage you to ask questions too. So just raise your hand or shout your question. So don't be shy, because the only one who can be embarrassed here is me, not you. The topic of the talk is from cold, dense, baryonic matter to compact stars. I give it a subtitle, and actually the subtitle hits it much better. It's Astrophysical Constraints on the Nuclear Equation of State. And as you will see, there are brackets around astrophysical, because for dense matter, neutron stars are very dense objects, we have more than astrophysical constraints. And due to the uncertain nature of neutron stars, in particular about the inner region, which is very dense, we do not know what exactly is in a neutron star. So that's why it's not given by nature or by some law that it has to be nuclear matter. It can be some exotic kind of state. When I've been asked to give a lecture here, I asked, okay, how many students, so what kind of audience? So I've been told there will be students. And I try to adjust a bit to that. So what I will do is that I give a presentation in 2 parts. The first part, which probably will consume the next hour at least, is very general statements about why neutron stars are interesting, what they look like, how they are built up, and what we can learn from astrophysics and here from heavy ion collisions. I will make short remarks on everything, but altogether it will take some while. The second part is a bit more theoretical, but still it's suited for students mainly. So only in the very, very end I will make comments on what I'm actually doing at the moment and what I'm really interested in. But this comes at the very end. So maybe I managed to scare you away until then. Maybe not. We will see. Okay. Neutron stars. Neutron stars are born in supernovae. And one supernova mankind took notice of happened in the year 10,054. It was visible from the Earth, and it must have been a very impressive view. It was visible with naked eyes, so some days a thing popped up on the sky. It was visible for quite a while. It was 23 days. But that's not what impressed people really much. What impressed them so much was that you could see it at daylight for 23 days. So there was a star on the sky, and I think it was a tremendous view. And so the way I plotted that, of course, it's just a dot I plotted here, but that's how it is described. So it was a bright, whitish, yellowish light, and if you put your arm away, it was the size of the nail of your little finger. That people have been impressed is really proven. So there have been records found in China. So this is a big plate of stone, and something is carved in here. Supposedly is that supernova. In the Middle East, people wrote about it. Unfortunately, I can't tell you where they write about it because I'm not very fluent in Arab. And even in America, which was not very developed at that point, people painted something on the rocks. Amazingly, Europe missed it completely. So no notice about that supernova in Europe. There's some hypothesis about it. In that year, in 10,054, the separation between of the Roman Catholic Church began. So, and people probably took it as a bad sign that there's something on the sky, so they just ignored it. It's one hypothesis. You can look it up, actually, 10,054, so that's the beginning of the separation into Roman Catholic and East Church. So the Orthodox Church, that's what Greeks and Russians had. Nowadays, we are still impressed, but we can still look at it, and much better, actually, than in the ancient times, so we can watch the remnant of that supernova in the Crab Nebula. We can watch them in the optical domain, in the infrared. We can look at the X-ray signals, and we can take it all together. And this gives a very obviously a very complex and structured system, which one can think about. But actually, that's not what I am interested in. I am interested in a thing here in the middle, which is the Crab pulsar. You see it a bit in the in the X-ray. And what we know about Crab pulsar now is really not much. It's his age, and we know that it rotates. It's a pulsar. We don't know how heavy it is. We don't nothing about the radius of that object. We don't know how bright it is because you have all that other stuff around it so that you can't make any statements about Crab itself. We don't know anything about the magnetic field, and that looks actually like a quite bad situation. So it would be nice to know more. So, yeah, okay. This is what we see. So within all that beauty, this is what a neutron star guy gets. It's not much, it's a bit depressing, but okay, it blinks. This situation is quite common for neutron stars. So in principle there are several observables. So there are mass observables. We know that the mass is probably about the maximum mass a neutron star can have is about 2 solar masses. Typical neutron stars have a much smaller mass. It's 1.35 solar masses. We know about the radii, so they are a bit larger than 10 kilometers. The maximum will be 17 kilometers under very special conditions. We know about the surface temperatures of...
What sets the maximum? What sets the maximum size? How do you get the maximum size?
You can observe it.
Just observe it?
Yeah, you can observe it. What you observe, I will speak about that later. But yeah, I will come back to that question. You can observe the surface temperature that you can know, and obviously the age. Actually, not of all objects, which is interesting too. You can measure the redshift of these objects, and these redshifts can become obviously very, very, very large. And of course, you have information about the rotation and of the decrease of the rotation, so the breaking of a neutron star, how it slows down, which is a very small number, as you see. It's 10 to the minus 9, 10 to the minus 21. Of course, for a person who is interested in understanding neutron stars, it would be nice to have all this data available for a single object or for as many single objects as possible, but that's not the reality. The reality is that we have some of these data for some of these neutron stars, and even in the situation where we have good data or more data, not all of them are undoubted. So there's always big discussion amongst the experimentalists, is it valid data or not? So that's the situation. Incomplete. So we don't have the full information for a single object on in the whole universe. And still we can learn from this about matter at supersaturation densities, and I will speak about how. So why is it important? So this here is an emerging neutron star system calculated by Wroclaw and West quite a while ago. There are systems which are similar, and they are on Earth. And these are heavy ion collisions. So that's a plot of the calculation of a heavy ion collision. It's gold, I think. And if you look at it, of course, the scales are quite different. So this is a small object. It's 10 femtometers. There are only a few nucleons in it compared to a neutron star, which has 10 to the 57 instead of roughly 250. But if you look at the densities, then this here comes up to 4 times saturation densities, even more. And this corresponds to the central densities you have in a neutron star. So that's up to, at most, 9 times saturation density. Actually, it can be less. And the constituents of that matter are, of course, the same. So it's neutrons, protons, electrons, muons, and whatever exotica you can have. So same constituents, similar densities, just different scales. That is actually very good news, because it says it's the same physics behind it. So the physics in a neutron star should be somehow correspond to the physics in a heavy ion collision. Which means if I understand these objects, I can learn about these. If I understand these objects, I can learn about these. And I can try to find inconsistencies, and that's the whole approach I'm following. Yeah, why are people interested in heavy ion collisions? So one of the reasons is that you want to learn about the origin of elements. So why we have as many elements in the universe as we have, where do they come from, how do we describe their masses, their energy levels, their shapes, drip lines, and so on, and of course, how general is our understanding? So can we apply our model really to every nucleus? Actually, we can't, but we will someday, of course. And so basically, we want to understand this nuclear landscape and the distribution of elements. There's one famous formula written down already in 1935. It's the semi-empirical mass formula by Weizsäcker. It gives the binding energy of a nucleus at saturation density. So saturation density, it's because matter is saturated. So it has been roughly at the same time developed by Bethe and Bacher as well. That's why it's often called Bethe-Weizsäcker formula. It has been updated a while later by Myers and Schwertetsky, and there was a reason for that. So what does it say? If you speak about the binding energy of a nucleus, there are certain terms which you have to take into account. One is a volume term, of course. The more particles you have, the more bound it can be. There's a surface term, because on the surface things can happen, so particles don't interact as they would do in bulk. And the next thing is that you have to take into account that actually you have different amounts of neutrons and protons in the system. So that can affect your system too. So this you do by this part here. On top of that, of course, protons are charged particles, so there will be a column interaction term. And if you want to do a real good job, and this is what Myers and Schwertetsky did, then you have to account for pairing of nucleons in the nuclei. So this formula works amazingly well. So you can look at the difference between experimental values and model values, and you will see that there are only minor deviations. So it's 4 MeV here, and here in the extremes -12, but in average it's really clustered around the 0. And so this mass formula has been evaluated for lots of nuclei and isotopes. So here, up to 2003, probably there was a new mass evaluation. I don't know whether that formula has been adjusted since then, because I just want to make some general statements. I didn't follow that further. So, but here it's 2,200 atomic masses, so that's a lot. And all you need to have in order to get this accuracy of description are these 2, 4, 6 parameters to describe them. There are more refined versions of that mass formula, but this is the most simple one, and it works surprisingly well. Of course, if it works so well, you can think about what happens now at large nucleon numbers, because this here are rather small numbers. Yeah, it's only 140, 160. What about a really, really huge nucleus? So you can go into the large A limit. Say, let's have that A going to infinity. You look at the energy per particle, and you do the same. So you look at the energy per particle. And what you will find is that you have here a constant volume term, the bulk term in symmetric matter. Here you have that symmetric correction, so for asymmetric matter, which is important too. And you have other terms, but all go with 1 over A to some power. So this goes with 1 over the cubic root, this one too. Here's some correction, which is interesting because it does not go with 1 over A, but it goes with A to the 2/3. So that's the column term. And this one is important because it would diverge if you let go A to infinity. If you let, however, you have the delta here, and delta is just the asymmetry of the of matter. So if you let that guy go to 1, this term would drop, and that means you have pure neutron matter. So in that case, you can take the limit for pure neutron matter, and you get an energy per particle which is positive, which means a large neutron system is unbound. And this is what we know. So we don't have infinitely large nuclei. However, what about neutron stars? Neutron stars. So this is a big chunk of neutron matter. Of course, we have forgotten something here, and this is the gravity term, which looks very similar to the column term. If you add that term, you add some negative energy, and the whole thing will get bound. And will get bound, oops, where's the number? Ah, yeah. So you can estimate, you can calculate that number, and you will see that for nuclear number greater than roughly 10 to the 55, you will have stable neutron matter, just bound by gravity. So, and that's an example for a very small neutron star. It's not very fancy physics behind here, but actually the magnitude is almost right. So it's 0.1 solar masses. It's a very nice, very neat introduction to the physics of neutron stars. That's why I wanted to show it. Of course, many things need to be and have to be done better. You have to take into account general relativity because these objects are very dense, very compact. You have lots of energy at the same space, so you can expect that relativistic effects will play a role. Of course, neutron stars are not pure neutron stars, so you have a finite amount of protons in it. This amount is small, so less than 20% mostly, but finite. And of course, you have densities beyond saturation density. So it goes much higher because you compress matter. And that's a point of actual research and lots of debates. So if you go to conferences, physicists cry and fight about it. Are there other states, exotic states, more exotic states than neutron matter found in the inner core of a neutron star? And yeah, I will speak about that in the very, very end of the second part. So conclusions of that. Neutron stars are laboratories for the equation of state over a wide range of densities and asymmetries. There is no equivalent on Earth. So the no equivalent is an important point, because what we have here is a special condition. So these small proton fractions you don't find in heavy ion collisions. Heavy ion collisions, if you collide even very asymmetric nuclei on each other, are roughly symmetric. So you always have roughly the same amount of neutrons and protons. It's different in a neutron star, which is very interesting if you think about fundamental concepts of how matter interacts. Okay, let's start with improving that simple approach. So how we do that? Space, time, and matter are related via Einstein's field equations, so obviously we have to solve them in some sense. On the left side of the field equations you have the Einstein tensor. It's defined by the metric, whatever metric we choose. And on the right side you have the energy momentum tensor, and this one is defined by the equation of state. Of course you can't solve that exactly, so you have to make approximations. In the following, the approximation will be always the same. You have a non-rotating spheric neutron star, so it's really just a billiard ball, nothing more. On the side of the energy momentum tensor you assume hydrostatic equilibrium. You can go through the mass, and what you will get in the end is the Tolman-Oppenheimer-Volkoff equation. So this one is the basic equation you have to use if you deal with neutron stars. What does it describe? It describes the pressure gradient of a neutron star. This is defined here by, this would be the Newtonian limit, so that is what you get from ordinary gravity, and you have relativistic corrections to that. At the same time you can calculate the mass of a neutron star at a given radius. And what you do is you define a central pressure of the neutron star. The mass, of course, at that point is 0, and then you start to integrate that equation out. And at some point, the density of the neutron star, the pressure, will go to 0, and that defines the surface of the neutron star. At the same time, you will find out what the overall gravitational mass of the neutron star is. So it's not very hard. What you get then is, if you vary the density, the central density, if you do that for different central densities, you will get different masses, of course, and then typically you will get a curve like that. So you have small densities, you will get a small neutron star, you increase the density, of course you collect more energy into the neutron star, and you will get a more massive object. However, there's a saturation at some point, and then this curve drops, usually. There are some other objects, but that's not the point here. So what you can do then is you can do an analysis of the stability. So basically what you do is a perturbation on the system, you knock on the neutron star and see whether it will start to oscillate and calm down, or whether it will explode. That's what you do technically, or mathematically. And then you find that there's a condition which roughly says if this curve here starts to drop, the neutron star will be unstable. So if you knock it, it will just fall apart. It doesn't do so up to this point. So this defines that there is a maximum mass of a neutron star, and this is a very important quantity. So this is what we are after. What is the maximum mass of a neutron star? So you see that we are actually very far away, in that example here at least, or basically in every case, from saturation densities. So this is 0.16 per cubic Fermi. It's a very important quantity. If you don't want to remember that, I will write it down. Because I will speak often in terms of saturation density. So the good question now is the maximum neutron star mass sensitive to the equation of state, and if it is sensitive, in what way? And to answer that question, I will write down something which looks like a generalized Bethe-Weizsäcker formula just in a medium. And this term you actually have seen already. This corresponds to the bulk term in the Bethe-Weizsäcker formula. So you had that AV, that was the first term, and you had another term which was called AS, which accounted for the asymmetry of the object, or the symmetry, however you want to call it. The only thing I do here is that I generalize it, that I say, okay, the energy per particle will change with density. So I can't expect that it will be always saturation properties, the same value as of a nucleus as we find them somewhere here. But so this energy can change. What you can do then is that you expand that whole quantity. You can expand it around saturation properties, and then you get exactly that term reproduced, which you had in the Bethe-Weizsäcker formula, and here you have a similar term. So now you can look at state-of-the-art equations of state, or more or less state-of-the-art equations of state, and see how that values look like. So you can understand this expansion here again. So this is at E0 as a function of density. If you expand it, the first order term gives you just this value, so that's the binding energy of symmetric matter. You get a correction, which gives you the curvature here, and you get a next order term, which gives you the cubic component of that expansion. You can do the same for the symmetry energy. And again, you have a constant value here, which is J, and you have a next order term, which gives you the gradient in that point. It's not so easy, actually, to do that. Okay. If you do that expansion and look at different equations of state, you will observe the following. At saturation properties, all these equations of state describe roughly the same value. So it's minus 16 MeV. Why is that so? Because the equations of state have been built to describe exactly that values, and it's a value we understand. So this is an experimental known quantity. The next order term, which is called compressibility, so the curvature here, differs already a bit. And the experimental value is not well settled, not as well as this one. So it changes a bit too. The amazing thing now is that if you look at the next order term, which describes basically the changes at very high densities, which are important for a neutron star, you have differences already in the sign of that quantity. So it can be negative, minus 716, or it can be positive, 500, no, the highest here is 576. So that should give you an idea how uncertain things are in that domain. For the symmetric parts, for the asymmetric corrections, the similar situation is similar. So the first order term is roughly known. It's between 25 and 35 MeV. The model is adjusted to reproduce that, but here you will find difference of order 2. So what does it have to do with neutron stars? That's a good question, which I will answer straight. The mass of a neutron star is correlated to that first term, which describes symmetric matter. And that's actually a surprising thing. It's not what you would expect, because it's a neutron star, so that mass of a neutron star should somehow be responsible to the whole equation of state. But actually it doesn't matter so much what you do with that asymmetric corrections on the equation of state if you are looking only for the maximal mass of a neutron star. So what does it mean? You can see that correspondence here, 1-to-1. You take an equation of state, just that first symmetric part, and you see a stiff equation of state, so a strong slope, corresponds to a high neutron star mass. If you have a rather soft equation of state like this one, you will find a neutron star mass which is lower. So you can take some intermediate values, and it's really almost a 1-to-1 correspondence. So that's our hope, how we can learn something about these not well constrained high density terms in that expansion, for instance, just from the neutron star phenomenology. However, we need to know large neutron star masses if we want to know something about the maximum stiffness of that whole thing. So these large neutron star masses are interesting. They provide a serious constraint on the equation of state. And that's what I will speak about in the following a lot, so about how we obtain neutron star masses, or different methods for that. So an example for a neutron star, of course a famous one, is the Taylor pulsar. So for its discovery there was a Nobel Prize given in 1993. About that object we know the spin period. It's a double pulsar. The orbital period is known. You can measure the decrease of the period, and you can compare the measurement, these dots, with what is predicted by general relativity, and you will see that this is an amazing so this result is amazingly precise. So the masses of these objects are known now to many at a very high accuracy, and you see how the accuracy increased over the time. That is because you had to measure the decrease of the period of that system. So this quantity here, this is what you measure, this one, this curve. As more points as you get, the more precise you can be. So it's obvious because if you have only a few points here, you don't have the general behavior. But as more points as you get, the more precise your result will be. And this is reflected here in what we know about the neutron star mass. And that's a general thing. So there are good perspectives to get more precise insight just by waiting, at least as a theorist who is not directly affected with, involved into the measurement. And so all we have to do is wait. So the statistics of these objects will get better, the data will be more precise. So meanwhile, there are lots of neutron star masses measured. Usually this happens, or actually it always happens in binary systems. So, but that's easy because, of course, you can't weigh an object which is just floating in the room. So you have to know some relation between it, and usually you do it via Kepler law and so on. So that's why these are binary systems. And what you see is there's something like typical neutron star masses. So these masses here, for instance, are very well known. It's all about between 1.3, 1.4 solar masses. There are some other objects with larger error bars, which depend, the reason for that is in the nature of these objects, so it's not so straightforward to do this. This here is the Hulse-Taylor pulsar. So you see, even though there was a Nobel Prize given for its discovery, it's not a very particular interesting object, just by the mass. So what we are after are high masses. If you look at high masses, you will see that the error bars are pretty huge. And that's a problem. However, there are good news. Here is hidden an object which has very small error bars and a rather high neutron star mass. And I will speak about this one. So this object is called pulsar J1614. It's a binary system in Scorpius. It's a binary because it's not only a neutron star, but a white dwarf too. So they orbit around each other. It's 1200 parsecs away from Earth. And it's a millisecond pulsar, just to give that information. So how you measure the mass of that object? So the effect is called Shapiro delay. Shapiro delay simply says that the time signal of the pulsar, as we measure it, is getting delayed when it's passing a near massive object. So this is a double star system. There's a white dwarf, so the time signal can pass the white dwarf if we are lucky, and delay the signal. It's a general relativistic effect, and the size of the effect depends on the mass of the neutron star and of the object, and on the inclination angle. So the inclination angle just means how directly we look at on the axis of neutron star and white dwarf. It's obvious that this pulse delay is best to measure when the pulsar is exactly behind the companion and we are in front of it. So this is illustrated here. This is the pulsar, this is the white dwarf. Pulsar is directly behind the white dwarf, we are somewhere here, and there's a huge delay. So actually it's not so huge, it's in the order of microseconds. So this is a unit here. So then the white dwarf moves on, the pulsar moves on too, there's some intermediate stage, the delay gets lower, and then finally if the white dwarf is behind the neutron star from our point of view, you have the smallest value for that curve. So this was a very precise measurement, and it led to a very precise result. The reason for that is that the inclination angle is 90 degrees, so almost 90 degrees, 89.17. That means that we really directly look onto the axis of neutron star and white dwarf. That was a lucky coincidence, very good for science. So everything could be measured perfectly. The companion mass is 0.5 solar masses. The neutron star mass is 1.97, which is nice, but we had objects like that before. But the remarkable thing here is the accuracy. It's 0.04 solar masses. It's a very precise measurement, and it's world or universal or intergalactic, however you want to call it, for a neutron star record, both in height, so in the absolute value of the mass, and in the precision. So the highest well-known mass before with a similar precision was 1.66. So this is a real increase in quality which we have, and we try to make good use of it. There's often a perception that all a neutron star person needs to know is exactly that. So what is the maximum neutron star mass? Then you build your equation of state and try to make it stiff enough so that you can describe massive neutron stars. Actually, there are more constraints, and I want to speak about them a bit more. If you start getting bored, just tell me and I can skip a few, because there will be a couple of. So besides the mass, there's another interesting quantity, which is the radius. But the radius is not directly accessible. You can imagine that. So, I mean, you speak about an object with a size of 12 kilometers, and it's 1,200 parsecs away. So that's something like 5,000 light years or so. It's really far, and it's almost impossible to just measure the radius of that object. So, but what you can measure are mass-radius relations, and that you can, due to the fact that these are general relativistic objects and they are redshifted. So that redshift of a neutron star is very important because it connects mass and radius. So in that, in this case here, for this object, HERX1, you can determine from gravitational light bending. So since it's a compact object, light will bend around it, you can calculate the redshift, and this gives you a relation between mass and radius of that object. So that would be one example how to do it. There are other ways to do it. So WCU has done it in 2006, Cotton before in 2002. There are predictions that the line shape, so the emission spectra of elements will change if they are in strong gravitational fields. And this has been measured, and it has been claimed, so it has been observed only once, but it has been measured for iron. And people deduced the redshift for that whole thing. And they measured a few other things. So the maximum flow during bursts, which is very important, and the cooling flux from burst to burst. So that's the thing that happens from time to time. And this gives you the possibility you have 3 unknowns and you have 3 observables. That's perfect. So the unknowns are the mass and the distance and the radius of the objects, and these are observables. So Eddington flux, cooling flux between the different bursts, and the redshift. So if you do that analysis, you get again a mass-radius relationship, or you get a clue where the mass and radius are. Another way to calculate mass-radius constraint comes from quasi-periodic brightness oscillations. So from time to time, a neutron star just flashes a bit, and then that flash is flickering. So there's a slightly flicker on it. And people try to understand where that flicker comes from. So it's called a quasi-periodic brightness oscillation, and it looks like that. So usually it's a double peak structure. It's actually not completely clear why it's a double peak, and it's not completely clear whether that the arguments which I give now are correct. The idea basically is you have a rotating neutron star, you have that burst, and either you erupt some matter into the surroundings of the neutron star, or you have an accretion disk around it. However, you will have some lumps of matter, so some lumps. And so those will circle around the neutron star, and you have the frequency of that pulse you measure. So if you have 2 oscillations in superposition, you will have a beating effect, so you will get a beating frequency. And this is what people claim explains that quasi-periodic brightness oscillation. So this peak comes from that beating effect, that beating frequency. However, there are other explanations for that, so you have to be a bit careful about this one. You can make several of assumptions here. One is for a peculiar thing about general relativity is there's something like an innermost stable orbit for an object rotating about around a neutron star. It's different in Newtonian mechanics. In Newtonian mechanics, you always can produce a stable orbit, no matter how far you're away from the object. So that's not true in general relativity. There is an innermost stable circular orbit. So if your particle goes below that threshold, it will just spiral down. So no matter what, no matter how fast it was before, it will go down. It will go down very fast. And this is used sometimes too, because that means that one of these peaks here will get broad very fast, because you can imagine that the frequency of that object changes very fast. So it's not a stable frequency, but it broadens, and then it will go away. And that tells you that you have reached that ISCO frequency. So if you take both together, one's a pumping model, which gives you a constraint on radius and mass, or that ISCO constraint, which says, okay, I reached that limit. So I can identify that this maximum here corresponds exactly to that ISCO frequency. This would give you a constraint on the maximum mass by itself, or on the mass of the object.
Does it depend on how the neutron star is rotating? In the most stable orbit 6, the mass is just about, is for the non-rotating neutron star. If neutron star is rotating, in the most orbit is closer to the object.
Yeah, probably it is, but usually even if neutron stars rotate fast, usually they don't rotate fast enough to so that that effect really has an impact on the analysis. But so I'm definitely not a specialist on that. It can be that they take those effects into account. So I just want to give the general
in a black hole case,
picture.
The effect is enormous.
Yeah, but these objects are way more massive, so. Yeah, of course, you have a great correction because the mass is huge. Another very interesting one, which will appear in the following two without being mentioned so far, is this one. It's RxJ 1856. This one is interesting because the temperature of it is very well known because it's almost a perfect black body spectrum that it emits. So if you have a black body spectrum, you can calculate the temperature of the object quite easily. It's very straightforward. So all you need now is to know the absolute luminescence of that object. And in order to do that, you have to know the distance. So that's easy too. If you have a candle close in front of your face, it's very bright. If you take it away, it's less bright. So it's important to know in which distance it is to calculate the actual luminosity of that object. There have been two measurements, one in 2002, which gave 60 parsec, and that had to be corrected 2 years later. So this is the claimed distance. And this just means, no, that means nothing. And so what people have done then is to calculate the photospheric radius of that object. So what does photospheric radius mean? Photospheric radius means just that it's the apparent radius. So if you would look from here on a neutron star, this is the radius you would perceive. However, we are living in the world of general relativity, light bends, so that means you get always a bit information from here. So and the more massive the object is, the further back you go. So, and the object appears to be larger than what you would have for the actual object, just by that. So that means there's always a correction due to the mass, and this is what you see here. So this is the photospheric radius, and that's at 17 kilometers I had in the beginning, where you've been asking about. Remember? Yeah. Okay, and okay, so the more object, the more compact the object gets, the smaller the actual radius of the object will be. It will just appear to be big. So, and this is the biggest object known. That's why it's an important constraint too, because it's mass and radius which you combine. What else do we have? That's an interesting tool. It's another double pulsar system. So there's a pulsar A and a pulsar B. And the progenitor of this, of one of both, I don't recall which, wait, it's this one. So the progenitor of this one has been white dwarf. And that white dwarf accreted mass. And it accreted mass so much that the elements in that white dwarf began to capture electrons. So the pressure became strong. Electrons basically are pushed into these elements. That's called electron capture. So here it was magnesium and neon. And the particular thing about this kind of white dwarfs is that they all look the same. And there's a limit at which you don't have so few electrons that you don't have Pauli pressure anymore. And that's what keeps up a white dwarf. A white dwarf is kept up or kept stable by the degeneracy pressure of electrons. So if you take the electrons out of the system, that system will become unstable and will turn into a neutron star. And exactly for that object, the mass of a white dwarf, which happens to be heavy enough to make that, to become unstable, is very well defined. It is defined by the baryon number within, so the number of particles within that white dwarf. The next interesting thing about that is, if you investigate the collapse of that system, so how it collides, how it collapses, you will find that there's no mass loss. So basically there are no, so there's beautiful pictures about supernova with that remnant around it and so on, you won't have there. So all mass goes into a neutron star and stays there. So it's a very particular system. And in that case, you have been lucky enough to say, okay, this probably is an object like that. So on top of that, you could observe the gravitational mass, because it's a binary system, which you don't have often. So that means you know the baryon number within this object, which you can translate into a mass, and you know the gravitational mass. Both can be calculated, and the accuracy here is quite impressive again. Yeah, so it's 3 digits after comma. So both quantities can be calculated. This would be the gravitational mass. This would be just the baryon number as you calculate it, and you convert it into a baryon mass. If you do that and compare different equations of state, you see that if the accuracy is really as high as this would be a highly distinguishing constraint, which actually puts the lots of equations of state which I would favor into trouble. So there's not a good agreement. However, this is on 1% accuracy level. So these equations of state would fulfill that. So the gravitational mass has this value, baryon number is this value of the neutron star. If there is a difference of 1%, so if this is not precise as it's claimed to be, then you would describe more equations of state, and if you make it a bit more unprecise, you see, then it becomes a quite general feature. So here accuracy is really important, and some people doubt that they could calculate it with that accuracy, or they could measure the other value with that accuracy. Anyway, observations like that might happen in the future again, so it's good to be aware of that there is something like that, because it really has a very distinguishing character. So that would be a short intermediate summary of what we had. So there have been the QPO results, which gives mass radius constraints. That ISCO result gives a maximum mass constraint. I don't speak about that recent pull pulsar. And here is that mass radius limit of RxJ 1856. So this is what we have in the mass radius diagram. If you calculate an equation of state and you have the mass radius relations for it, each region here represents a different object. And in consequence, if you have a mass radius curve, that mass radius curve should touch every of these objects at least once in order to be a general model which describes all data we have. I want to make a remark on at that point. The maximum mass, as I said, depends mainly on the energy per particle in symmetric matter. The radius, however, is very sensitive to that correction due to the asymmetry of the object, and that becomes important. However, right now, since we are interested more in that maximum mass, I will speak a bit more about symmetric matter. So we had that in the beginning already. Another system which we produce on Earth are heavy ion collisions. So this is mainly symmetric matter. Since the mass of a neutron star is determined by that symmetric matter constraints, of course you can ask what can we learn from heavy ion collisions. And actually at the moment not much. There's only one study I know of which would really give a deeper insight, and I hope, actually we're working with this guy who did it, that we can improve on that. So what did he do? He looked at the elliptic flow of nuclear matter in heavy ion collisions. To give a short explanation, actually you see it here. So if you have two colliding nuclei, you see that you have spectator particles here, which might prevent matter from flowing into all directions uniformly. So it's more likely to go to the front or more likely to the side, but certainly it doesn't have to be a perfect spheric expansion. So, and that depends on the equation of state of the system too, and that's exactly what he did. So he put an equation of state into a code and tried to reproduce this elliptic flow data. And what he got out of that was a relation between the pressure and the density in symmetric matter, of course with some error bars. So the actual region he constrained reaches from here to here, And this here is an extrapolation I did because I was interested in another question, which I will come to in a bit. And you see that there's an upper bound to that region. Of course, you can extrapolate it too, and there's a lower bound to that region. And any realistic symmetric equation of state, so symmetric matter equation of state, should go through that region. So it should not cross it, because then it wouldn't be in agreement with these data. However, be careful, that calculation has been done once only, so it's not clear whether that is the final truth, even though he tried his best. So now you can look what happens to some of my favorite equations of state, and you will see that actually some of these equations of state leave that region, so they go out. Unfortunately, those equations of state are those which produce the most massive neutron stars. And it's almost a problem. So,
can I ask a question at this point?
Yeah.
You say that the symmetric part of the nuclear matter is the one which determines the maximum mass now.
Mostly, yeah.
I mean, however, it's a stiffness or non-stiffness is manifested in this pressure, this density, right?
Yeah. So here it's represented. Actually, it's not a trivial.
Yeah, it's not.
It's not a trivial representation. I mean, you can look first into really the energy per particle and see which equation is stiffer, and then you will find that those which run on the upper part are the more stiff equations of state.
However, the pure neutron matter, the pressure of the pure neutron matter, is related to the symmetry energy.
Exactly. Exactly. So
that. Somehow that correlates.
No, it doesn't.
It doesn't?
No.
So why?
The point is that the pressure becomes important at small densities, and it becomes important because it builds up. Now you can imagine that it gets harder if you change the pressure a bit to compress matter in the outer parts of the neutron star. In the inner parts, the corrections to the energy per particle are just small. No matter what asymmetry you choose, it's small. So it's 20%, you square that. So it's really a small contribution to the overall energy per particle. But energy per particle, that's mass. That's mass generating. So it has a big impact on the radius, but a small impact on the actual energy you accumulate.
But on the other hand, the stiffness, the stiffer it is, the mass, I mean, there is a stiffness.
Of course, I mean, the pressure density relation in neutron star matter will look different. So I don't have that contributions in here. So this is an artificial way no, not artificial. I just extracted the symmetric part of the equation of state I used. Yeah, it's just this pressure and symmetric matter. For a neutron star, I would take that corrections into account, of course. Yeah. It doesn't work without.
One more question.
Yes.
I'm not trying to ask the most stupid question, but I mean, if I ask the most stupid question, I help myself. I get my from myself, so it doesn't matter. But the statement that the neutron proton asymmetry gives you the radius.
It affects the radius, yeah.
It affects radius.
Yeah.
So the statement is made, I heard this statement last week, the week before, that if the measurement done at the JLab of a very precise radius, the neutron proton radius difference in lead-208 has something to say about the
radius
size
Yeah.
Now, how does that come in? I mean, independently of the density, because the density is rather low there.
Yeah, but that's exactly the point. So the radius goes over the whole. So most of the mass of a neutron star is not accumulated in the crust, but in the center. So that's why that energy is important. So the radius is determined in the low energy part. So, and that's why it's important to have a very precise understanding of the symmetry energy. And this is what you address too if you measure neutron skin thickness and stuff like that.
Is it direct relation, or is it complicated? You have to go through a complicated
between radius and pressure, or
the radius of the lead-208 at the JLab experiment and
I don't
neutron star radius that
I don't think it's straightforward. But maybe there are some people smarter than me who thought about that. I don't know.
In other words, that there is some kind of relation.
I know that for neutron stars, there is a relation between the radius and the pressure to the, I don't know, 1/4 or so. So Latimer made something like that. So which is surprisingly constant for different equations of state. So, but how you translate that directly into neutron, into nuclei, neutron skin thickness, I don't know.
Yeah, because I saw in the curve some pictures giving the plot of neutron, neutron proton size difference.
Yeah, I mean.
On the graph.
Okay, let me go back shortly.
There is one somewhere.
Yeah. So if you look into this one here, I mean neutron skin thickness certainly depends on this part here.
Yeah, that's right.
Yeah, and you see that is probably rather, at least for that kind of models here, it can be rather constant. However, some people claim that the symmetry energy has a very exotic shape. Yeah, it goes up here and comes down at higher densities. So Baoan Li is doing that, for instance, the super soft symmetry energies. So that's why I would be very careful about statements which directly connect neutron skin thickness and the radius of a neutron star, because the uncertainties here are just huge, and there can be strong model dependencies. So I would be careful.
One more question at this point. That expansion over epsilon, this the expansion.
Yeah.
Epsilon. So epsilon is defined by the mass density difference between.
Yeah. So it's an expansion around saturation density.
Right. And if you go up to 0.5 for the cube, then epsilon is about it's near to 1.
Yeah, so this is.
So is it meaningful to draw, or is it?
No, and that's actually a very, very important insight you just had. It's not meaningful at all. The interesting thing is, usually the stiffness, for instance, of an equation of state is measured in terms of K. So people say if I have 200, it's or 150 or whatever, it's soft. If it's 300, it's stiff. But that does not necessarily mean that the neutron star equation of state is stiff in the sense I speak about stiffness. So stiffness for me means large neutron star mass or stiff behavior in the large density domain. So not in that small region around saturation density. So I can still have the same curvature and so here could be variations in the high density part. So it's very important to keep that in mind. So you can fix your low density or your saturation density properties, but still have completely different behavior for neutron stars. Yeah, okay, since we have been there. So these are the same equations of state. Just remember that red one here, for instance, that red one, remember that there are some blue lines and the black ones. So blue, red, black. And if you look at the flow constraint, you will find the same blue, red, black. And this corresponded to the very massive neutron stars, while black corresponded to the less massive neutron stars, which are in trouble with that maximum mass constraint. And you will see actually you can't make your neutron star equation of state just as stiff as you want to in order to get the mass high if you want to be in agreement with a flow constraint like that. So it's a pretty severe constraint. You constrain the stiffness of the equation of state from the lower side. So there's a minimum stiffness just defined by neutron star masses, and there is an upper limit on the stiffness by this flow constraint.
But there is a strong assumption that the simple extrapolation should work up to the higher density.
Yeah, it's wrong. I mean, of course, you can make always a Taylor series and so on, but how you control it?
So the phrase that the equation of state that satisfies the low density constraint
on the neutron star side?
The neutron star side.
Yeah. No. No. So not in a strict sense. I mean, of course, you can't do whatever you want to. So it's not that it's completely unconnected, but these connections are non-trivial. So you really have to look into it, whether it agrees or not. but just to make some extrapolation always is a dangerous idea.
Yeah, but you see that Latimer and company extract those factors like L and other things by looking at the heavy ion experiments and also neutron star experiments and so on, observations and so on, and they give you some bound somewhere, right?
So
narrow area.
yeah.
Does that is it relevant to neutron star physics?
I think the things that distinguishes the approach Latimer and I have is that I really try to be blind to models. I don't want to see models in my conclusions.
You differ from Latimer.
Yeah, we in that point we have a different opinion, probably, as how it should be done. I think all we have are measurements or observations, and we should just see whether it fits or not, and don't try to be too brave in our conclusions, because I don't see that there are any strict or strong derivations of stuff like that. And model dependencies will be death of insight in the long term. And he does it a lot. That he starts from some simple model polytropic equations of state and so on, and draws some conclusions from that which hold in that model, and you don't know how far beyond.
Just a question: to which equation of states these two blue curve correspond?
These?
Yeah, I would say the two ones which are excluded. Yes.
These are excluded by this constraint because they don't touch that region, but they would very well agree with the maximum neutron star mass.
To which equation of state they correspond? Nuclear matter, quark?
It's all nuclear matter. So yeah, I don't. Yeah.
Yeah. Okay.
No, it's just so the models I considered. So what do we have? Basically, these are all Waleczka kind type models, except for this one here. This is Dirac-Brückner-Hartree-Fock, and this here was done by Voskresensky. So it's kind of Waleczka model. Actually, you use Brown-Rowe scaling to define that models. And this one here, DDF, this is this one. That's a brother of both of these, but so we improved it a bit in order. So that was in collaboration with Stefan Tüpel, who helps us a lot with all that investigations on the nuclear matter side. So he just so it's basically the same model as this one, just made fit to the flow constraint, and still providing sufficient masses.
Well, you said that at high density, relevant to neutron star, does not have, the equation of state which gives you correct, say, right order of the size and the mass of the neutron star, does not have to satisfy the constraints at the low density. I mean, it could be different, right? You're saying that
what I'm saying is that the stiffness, that you have to be careful about what you define as stiffness. So when I speak about stiffness, I speak about the high density behavior, which is almost a constant gradient for some models. While if a classical nuclear physicist speaks about stiffness, he speaks about compressibility. So for him, it's
so the blue curve, I mean the blue dotted curve, which you say actually gives a high mass.
Yeah, this gives.
So if you observe the high mass object, that's consistent with your high mass equation of state. Right?
Yeah.
But it doesn't go into the constraint given by low density.
So the interesting point is if you observe a very massive object, which next slide. Yep. Here comes the point. So what I did here was to extract the symmetric equation of state just from that upper boundary and from that lower boundary. Right. Then I took all symmetry energies I could get and calculated neutron stars a lot. So with different equations of state, where the difference just came from the different symmetry energy. So exactly that part. So really get an equation of state at high densities from heavy ion collisions. Obviously, it's possible. Obviously, it's difficult because nobody did it after that. And obviously, it's very, very important to do that. The other thing you see is that you definitely can learn from neutron stars about heavy ion collisions, and that I like a lot because I'm rather from that neutron star corner, so I can tell them, you made a mistake. And that's the lower boundary, because this would predict a neutron star of 1 solar mass, which is way below even the typical neutron star. So that means that lower boundary here is much too low. It should be somewhere, at least here. And of course, I couldn't resist. I went to Pavel and told him exactly that. You're wrong with that lower limit. And he said, yeah, actually I wanted to publish a higher limit, but the referee forced me to put it down because he didn't believe me.
Who is this LB?
Huh?
I mean, the lower boundary.
Lower boundary. It's just how. No. So that.
I mean, who put that there?
That's. I did that by hand.
Oh, okay.
This is L, lower boundary, upper boundary.
Yeah, but that corresponds to some theory.
Nope. Not at all. So this is the result by Danielewicz, this region here, and all I did was just to extrapolate it somehow in order to get an idea. But as you see, so this goes up to 0.65 or so, so it's not so far away from what we do. So here you have already, so this here is the upper corner. You see you're almost close to the 2 solar masses, so you gain about 0.1 solar masses for the real maximum mass. So it's quite solid. So actually I don't need that one. And the low density extrapolation I did, that really affects the radius, and I never show mass radius plots exactly for that reason.
Can I ask a question?
Of course.
Could you go to the next slide?
Previous?
Yes, previous. Yeah, this one. In this picture, all lines start from real normal nuclear density. But if we consider only Fermi gas, then pressure will start from zero normal nuclear density.
Yeah, it does. It's a very low density part, but this here is a logarithmic plot. So if I would go to 0, I would have to. Huh?
Then
Yeah.
lines go to zero.
Yeah. So pressure goes to approximately. So it goes to very, very small values, which are not so it doesn't change the physics or so. And they are all roughly the same. So at some point I have to do by hand a phase transition in order to describe clustered states. So a real nucleon equation of state and not a nuclear equation of state anymore. Because in the crust you would expect something like nucleons. So, and then it's all the same. But it's roughly here already. All the same. Yeah, no, not here yet. I think that wasn't a stupid question, though.
You're out.
Okay, so of course it's somehow mean that I push so much the point that from neutron stars so far we don't learn anything about the asymmetry energy. That's what we really would like to do, because the asymmetry energy is an important contribution to the neutron star equation of state. But really, from static properties, except for the radius, which you can't measure, you won't learn anything about the asymmetry energy.
But why can't you, okay, you cannot measure the radius directly.
Yes.
If you know the mass and you measure the ratio, then you get the radius.
Yeah,
You can also measure the ratio.
we don't. Yeah, but we don't have such. We don't have this datum. This is data. So there is no mass radius point known. You always have a mass radius relation. Which. Okay, I can show it later.
But the point one must consider is that the new bigger freedom, other than the nuclear, depends strongly on the symmetry energy.
Exactly.
So that's another
Yeah.
game.
Yeah, so there are lots of reasons why it's important to know the symmetry energy. Yeah, that will be private discussion later. Then I can say some more. So what about that second term? So that second term obviously defines the structure of the neutron star. So it's really affected by the number, the actual number of neutrons and protons you have at a given density. And the best candidate, or one of the best candidates I see at the moment, is the investigation of cooling of a neutron star, because the cooling of a neutron star is closely related to the internal structure. So cooling of a neutron star works basically always the same. You have some processes, you emit neutrinos from the inner core of a neutron star if the object is hot enough. So for a young neutron star, you will emit neutrinos, they are free. Mainly neutrinos. So and that can be here something like beta decay or modified beta decay. Actually, it's not called beta decay, it's called direct Orca process. So direct because it's just to distinguish it from the modified Orca process where you have a bystander particle in order to modify it. Yeah, there's so Orca process has been investigated first by Gamov. So he called it Orca process after a casino in Brazil, which is called Casino da Orca. And he said, the energy disappears in the nucleus of a supernova as quickly as the money disappeared at the roulette table. So
he seems to be happy though.
he was a very he's a scientist. He doesn't need money. Yeah? Look at me. So of course he was aware that people could ask what Orca actually means. So if you submit a paper and you get a referee report and you get the question, what does Orca mean? That's not a good explanation somehow. So he had the alternative explanation, which was unrecordable cooling agent, but he never had to use it. So it went through. Nobody asked about Orca, what it means. He just called it Orca process and it went through. Yeah, Gamov, it seems to be he was a funny guy. There's another achievement of Gamov, so it's the famous alpha, beta, gamma paper. And one of those, I think alpha wasn't, no, beta wasn't original author. So it was just the work of him, Gamov and alpha. And he realized, alpha, Gamov, there's a beta missing. And he knew beta, that's almost it. And that's why it became the alpha, beta, gamma paper. So beta never contributed to it. He just said, okay, if you need alpha, beta, gamma, I will be better. So that's how Gamov was ticking. Okay. But that's the Orca process, neutron to proton plus electron, and the emission of the energy actually happens via the neutrino. So then, of course, you have surface radiation, which becomes important for later phases, so for the late cooling of neutron star, where we really just cool the neutron star from the surface. There are some other exotic processes, and you can think a lot about it. It's a very dirty business to do that calculations. What has to be said is direct Orca is a very, okay, so how does it work? If you look into that decay and you say, okay, neutrinos actually are not, so there are no boundary conditions on the neutrino, so the process I actually have is that neutron decays to proton plus electron, then you have a triangular relation between neutron momentum, proton, and electron momentum. So this corresponds, so this is the Fermi momentum, which corresponds to the chemical potentials. Chemical potentials, of course, give you density of the system. So you can evaluate that relation and you can derive a threshold where that process is possible. And this threshold depends on the ratio of electron to electron plus muons, if you take muons into account as well. If you have no muons, it's 11.1% or 1/9. That's the classical Orca limit. And then there is the relativistic limit, where you take muons into account, and in the relativistic limit, electrons and muons have the same densities because the mass doesn't play a role, but it's really just driven by the chemical potential. And then you get a limit of 14.8%, which is, I don't know, 1/6 or something like that. You can get it here from that. So this in brown here is a threshold, and you see if you reach a certain density, you exceed that threshold, and at that moment, equation, so the symmetry energy will allow your neutron star to cool very fast via the Orca process, unless it's gapped somehow, which we don't know perfectly. So usually people just ignore it. If you don't ignore it, you have a serious limit here, which would disqualify some equations of state just by the fact that they cool so fast that it's not in agreement with any observation of neutron stars we have, which are cold, but not so cold as the Orca process would imply it. There are corresponding processes in quark matter. Possibly they are suppressed, but this is a conjecture, so it's not a conclusion or so. It could be that they are unsuppressed as well, so that doesn't solve the problem. It's an open issue. Oh. What you see here is that the proton fraction is directly related to the symmetry energy. So you have, again, and I like it to have stuff like that because it's really nice to see following quantities like neutron star mass of E0 or proton fraction as a function of the symmetry energy. So again, you have such correspondence. Interestingly, if you would plot beta squared ES, which is the contribution to the equation of state, so that beta was the asymmetry, then this would all bundle up. So most of the equation of states, so most of these different models would predict almost the same line, goes somewhere along here. So all these for sure, and some of, no, so these would drop out or so. So there's some kind of universal behavior of the actual energy contribution to the equation of state from the asymmetric part. Within certain limits, of course. It's not always true, but it's, for these models, it worked quite well. I just don't have a picture of that here. Okay, so that's again the same story here. It's a huge emissivity, cools the star too fastly. Why is that important? That's important because the question whether you reach that threshold or not, of course, depends on the central energy of the star. And it will happen for massive stars, mainly. So a massive star will cool very fast. And this is what you see here. So you have slow coolers, if you do a calculation like that, medium coolers, fast coolers. And at the same time, you can calculate the mass of a neutron star in some models. So this would be a light star, heavier star, even heavier star. But they all cool reasonably, so they would describe data. And then you have the direct Oka process, which kicks in somewhere between 1.8 and 1.9 solar masses, and zack, you're out of data. So out of the possibility to describe data. This situation actually is quite lucky because the Oka process doesn't happen for small neutron stars. You can imagine if this would happen for a 1.1 solar masses neutron star, all these data would be impossible to describe. So that's the strength of the Oka constraint. The unfortunate situation is that we don't know the masses of these objects, which is sad. So if we would have that, that would provide a serious constraint, because then we would have an information about the symmetric and the asymmetric part of the equation of state. But we don't have it. So this is really just asymmetry, and we have to guess what mass these objects have. And that brings me almost to the end of that first session. So another recent measurement, which is very promising for the future, is that of CAS-A. CAS-A has been observed over the last 10 years, and people have been able to measure a temperature gradient. And so over the last 10 years, if you compare that to this plot here, here you really just have a temperature somewhere in the temperature H diagram, and that's all you have to do. So you have to get an equation of state which somehow crosses these data points. Here it's different. Here you have to get the gradient in a very small interval, so which gives you very tight limits. So straight after that, a big discussion started about what does the neutron-proton gap look like in order to describe that constraint. Is quark matter ruled out now finally or not, and so on. So all that kind of discussions just triggered by that one measurement here. So it's a very important one, and it goes directly to the structure of the neutron star. That's why it's important, probably more important than the high mass neutron star constraint. But much more complicated to evaluate as well. And that's the summary, which basically says what I did. So I tried to give some motivation, first by Weizsäcker mass formulas, and I showed you how to get a simple neutron star, a less simple neutron star. I spoke about mass and mass radius constraints, heavy ion collisions, neutron stars, and a bit about neutron star cooling. And 1.5 hours are roughly over, so probably I can't force anybody to stay here any longer to listen to the second part.
Second part is very interesting. Okay, well, we have a break?
Yes.
We have, how long?
After some questions.
Yes. You can also ask very clever questions. Okay.
Can I have a stupid question?
Okay, clever question.
Can you go back to the previous slide? I mean, can I say, the graph between the neutron stars and the high ion cloud.
I can just go through and you say stop.
This one.
This one?
What is the NS that you wrote down again? The NS.
This one? Where it is?
What is?
It's if you look at, of course, if you look at a table or so, it has a certain density, yeah. But if you look at a neutron, of course, it has a certain density too, or a proton, and that's exactly what it is. It's the saturation. So saturation density means the density at which nuclear matter is saturated. so which makes it stable. So it's really the density of a nucleus.
How is it
Nucleus.
related in this graph?
Hmm?
How is it related in this graph?
It's just a value, and actually in that graph you don't see it because I'm interested more in the very high density behavior, so it's somewhere here. So saturation density, which is an extreme density. So you have to imagine that you take all the vacuum between neutrons and protons, which we have a lot here. You take it all away, put it together, it's extremely dense. And I compress it even further by a factor of 4 or 5. So nucleon and proton wave functions, for instance, should overlap already. So it's really an extremely dense system. Huh?
Saturation. The pressure should be 0 because it's stable. Yeah, it's mean. So if I go down, okay, this is logarithmic, so I should go to 1 or what? No.
No, it's not stable because now it's really the effective pressure. So you really compress matter to saturation density.
Right. But I think if I have this density, this is the pressure of the system. But if I go to saturation density, the stuff is stable, so I don't have any pressure acting outside. Do I understand it correctly?
I don't think so. But so that's now a very good question. No.
Or very stupid, but I do not know.
No. So I don't think that. So matter at saturation density is so a nucleus at that density, of course, is stable, but that's true in vacuum. So the overall baryon density, if you speak about this room, is close to 0. If I speak about the total density, overall density, which is around saturation density, it's not 0. So this is a basically homogeneous matter description here. So I wouldn't expect the pressure to be 0, because that would mean that basically we should collapse to saturation density, which we don't want to, because we would be dead.
Okay, but then there is electromagnetic interaction.
Yeah, there are lots of other forces. But I have to think about it in detail. It can be that I speak non-reasonable things here.
한국말로 우리말로 해도 돼.
No, you can ask him in Korean.
질문 없어? 질문? 스케줄 되지 않으려고?
So you did understand what I wanted to explain, yeah? So you got an idea, or yeah? Or not? It's all clear?
What did you say?
Can I ask one question?
Sure.
The upper bound and lower bound is obtained from only astronomical observation data?
No, so this is not astronomical at all. This is from heavy ion collisions. So this is the heavy ion part here. So this, this comes from heavy ion collisions. You really have colliding ions, and you can analyze the dynamics of that collision. And then you will determine pressure gradients in that system and so on. And from that you can derive a relation between pressure and density in a heavy ion collision, in symmetric matter.
But heavy ion is the nuclei. But this graph shows the nuclear matter, right?
Yeah.
But heavy ion collision shows the nuclei. So
Yeah, but you would expect, yeah.
nuclear picture is the same as nuclear matter?
At some point it should be, yeah. So of course, but if you compress it a lot, of course you dissolve the bound states. So nucleons are just nuclei are just nucleon bound states. So if you collide nucleons, if you collide nuclei, you will see the nucleon property during the collision, and that's what people try to do. So they take a nucleus because that's the only way you can get neutrons and protons. So you collide them. Then you hope that you have some kind of neutron-proton liquid or whatever in the center of the collision, and you try to extract the properties of the nuclear matter in the center of a heavy ion collision. And that's supposedly supposedly, in particular, the elliptic flow is very sensitive to how the equation of state of pure nuclear matter is made.
By the way, here, I guess that if this is coming from the heavy ion collision,
Yeah, exactly.
there should be some temperature dependence
Yes.
as well as some the momentum dependence and so on. How
Yeah.
did you extract the
I didn't do it all. Danielewicz did it. I asked him the same question. And he said temperature dependence might play a role here for whatever reason. So at the lower boundary. Might play a role for the lower boundary, but the lower boundary is already quite... no, so if you look at that error range, it's actually not small. It's almost a magnitude, half a magnitude. So it's quite large already. He said, the next thing he said, that the temperature dependence here doesn't play a role at all. So he looked into it, it's rather stable. So no matter what temperature he guesses, it doesn't play much role. Yeah.
What about the momentum?
And yeah, he does it. And he does it in a mystical way I don't understand completely. That's why it's really important that people redo it. So he has some momentum-dependent potential in order to describe the interactions and the flow. So it's in there, and somehow he managed to wet that momentum dependence with this kind of an effective model. So it's both in there. It's craftsmanship. So it's not a strong first principle calculation or so. He did lots of...
Maybe what he meant is maybe those momentum and the density itself is correlated, so that higher momentum produces the maybe higher density. So if you count density dependence, maybe the momentum dependence automatically counted. Is that the logic?
It could be, but really I'm not a specialist in that calculations. Actually, I was supposed to go to Michigan once for half a year to learn that stuff, and I rejected and tried desperately to find some other topic to do.
Okay, the students should be excused from the second because it's much more technical.
So that's the same.
Okay, so after I gave that constraint, so actually what survives from the constraints, if you really want to model an equation of state, is that what Chihiro said yesterday. It's that high mass constraint and its flow constraints. It's at the moment the most important thing you can think about. Maybe, so there's that mass radius constraint, which went to the very right, because it's really large radius for that object. There will be a plot of that, I will mention it again. That might be an interesting one too, but lots of people ignore it, so I don't know. Okay, let's speak about implications. So what are the consequences? That's of course a joke for students, not for you, so you don't have to find it funny. Can we know what's in there? That's the big question we are dealing with in particular. That's a chameleon. Yeah, and of course I thought about it when I chose it, because a neutron star is pretty much that. It's a chameleon. We don't know what it is.
By X-ray or?
I stole it, so don't. I just googled chameleon. I wanted to find a colorful one, but then I found that one, and I was so excited because it's exactly what we do. So we look into a thing which looks differently depending on your perspective, on what you want to see and what the environment is.
It's not drawing, right?
It's certainly not what?
Drawing.
No, it's not a drawing. Right?
No. I think it's an X-ray. Yeah. Uh-huh. So it's the most intimate look at the chameleon you can get.
Penetrating looking.
It doesn't look happy though. But it's well fed. Okay, so and with neutron stars it's similar. So they have different appearances, and not on the outer but in the inner part. So that's the distinction to a chameleon. So from the outer part we are pretty sure what it is, what it looks like. So yeah, I don't want to go through all of that. I can. So outer crust, ions, electrons. So that's a standard neutron star. And here in the inner part it becomes interesting. So the question is really, is it just neutrons, protons, some superconducting matter as well? Or maybe it's something very exotic, like strange quark matter, so that we don't have that nuclear layer at all, but really nucleons are burned up so eaten up by strangeness. This hypothesis works if strange matter would be the most stable ground state. I don't know whether that argument which pops up every now and then that it could be, whether it's really reliable. As far as I understand it, but maybe someone here has a good statement on that. As I understood that strange star business, it has been so that statements that strange star is the most stable ground state at high densities holds only in a certain class of models. So it's a back model assumption and it holds only for a certain range of back constants. So I'm not sure that there's any general statement which supports that hypothesis. So in particular, I don't know whether there are any NGL or other state-of-the-art quark matter models which would support that hypothesis. I'm not aware of any. The only models I see where that is described are back models.
If I take NGL, what is the amount of strange quark? If you take the usual NGL model for this
in a relativistic limit, it's 1/3, but yeah, but that doesn't mean that you minimize the energy per particle with that. Right. That's the point.
Okay.
So, and in a back model, you can do that. So you come up, you come down again, and then you go up.
And then you have more strange than up and down.
And then you have two minima, basically, and one minimum is deeper, and that's the strange minimum. So for NGL models, as far as I looked at it, there's not even a minimum. There's nothing. So
it's just quark matter, but not strange quark matter.
It's no. The problem about strange stars goes deeper. If it's really the absolute minimum, then you would have a transversion from nuclear matter to strange matter after a while, if you wait long enough. And that might happen in a neutron star. And actually that happens very aggressively. So as I understand, people who investigated that, it's really a burning which takes place. As soon as you have that first seed of strange matter, it will start burn out. So it will eat up all nuclear matter up to a certain minimum density. So it's not just that you have a strange core. A strange core we can have, that's not a problem. Or a core with strangeness in it. But this really is a pure strange being with a very thin layer around it. And that layer holds only because then you have strong electromagnetic repulsion from strange matter to the crust matter. So that the strange matter can't eat up the crust matter anymore. So there's a small gap between both. It's a very strange thing, the strange star. So the next thing is that strange stars, by our models which are known so far, so classical strict strange stars. So you can speak of such a thing as a strange star too, if you say there's strangeness in it. But so I mean that extreme model. And in this extreme model, strange stars usually are very small and not very massive. It could be though, and that's an interesting too. We know how it works if you look at the mass radius plot, and now you go into the mass radius. Let's say it's radius. So you start here from very low densities. Then you would have something like the sun. Then you have a region of instability, which somehow looks like that. Then it goes on. Then you here have neutron stars, white dwarfs, so roughly the same mass. Then you go into the next instability region. Then you come to neutron stars. And it could be, maybe, that there's a fourth branch, and that could be strange matter. Because there are some observations which imply that they are small and not very massive objects. And that would be in disagreement with what we know about neutron stars, because neutron stars are either large or massive. So, but if you find an object which has a small radius of 8 kilometers or so and a mass of 1.5, then you're in trouble. So, and that could be, and somehow it's referred to like that, a third family of compact stars. So, ordinary suns are not compact stars, but white dwarfs, neutron stars, and maybe a third branch. So if there is room for that, I'm almost convinced that the strange stars would form such a thing instead of being part of the neutron star family, because it somehow it doesn't fit. Yeah, it would be something completely new, and I don't see observational evidence for that. So there are indications, maybe. So.
One comment is that the MR curve for the strange matter is different from ordinary nuclear matter. So it goes like this. The other way.
Wait. Yeah, I've. Yeah, it would go like this.
Yes.
It would go like this, but if you go to strictly zero density, zero mass, that means you have zero density. If you have zero density, you're in the crust region again, So what you have is some transition here at that place, at that region taking place, and you would go again into that branch. That's how it works. Exactly. So it doesn't come from the right, it comes more from the lower left. But if you go to smaller masses, you have that. The next question is how to create that object. Same question actually for neutron stars. We know that actually you never come on that branch here, so you don't do that. Neutron stars are created somewhere here in supernova, and they accrete mass over time, and that's how you can access this region. But the typical neutron star is in that region, so that's how he is born. This here has to come from somewhere. So the next question is, of course, how to give birth to such an object. So you can't reach it via this region. Oops, most likely not. Okay, so but what I am interested in, of course, is this part here. That's the inner core. And there are lots of hypotheses, so what could be in there. So everybody agrees electrons and muons, most likely. Neutrons, protons, that would be standard, of course. Then you have hyperons, bosonic condensates, or deconfined quark matter. So what is it? Of course.
These two are the same. Hybrid and neutron star would be the same pulsar. But the last one wouldn't be a pulsar state. It would be something different.
Yeah, be careful with what I'm saying. So that's my point of view on the whole thing. I would claim that probably strange stars, if they exist at all, they would form a next branch.
Okay, something completely
different
from the other two.
Yeah, because all calculations you do for a pure strange star give small radii, small masses, and that doesn't fit with what we know how stiff the equation of state has to be for a neutron star. So then you have to decide whether you want strange star or neutron star. If you want to have both, you need to have two families. So that's the only solution I see, but that's my personal opinion. So it's not, I don't know, something everybody would tell you like that. So there might be different opinions on that point. Okay. So then again, so that would be, yeah, why is that pulsar so exciting? I mean, basically we got the lesson. So if you take different nuclear equations of state, you find some which are not heavy enough. Oops. Then you can look at the flow constraint with the same equations of state, and you will find that some of them are too stiff. And I tried to catch it roughly right here. So this really roughly corresponds to what the flow constraint actually constrains. And this is very interesting and almost depressing, because flow constraint and that Rxj here seem to be almost a bit in trouble with each other too. So, but I didn't look into quantitative results for that.
The only curve which fits perfect is this violet one.
We will see.
I mean,
yeah, for nuclear matter at that point, no, so this one here fits too, the blue one. So this curve here goes too far. It's just to say that if you are below that, you're out. So this one touches too. Right. However, that violet one, I mean, you could imagine you have an equation of state which goes a bit further up or a bit more to the right and up, then you would have this one too with the 17 kilometers. So that Rxj, so that photospheric radius has been measured by, I don't know who measured it actually, but the whole interpretation and so on was done by Trümper. So that's the former director of Max Planck Institute in Garching for astrophysics, and he is very convinced of that constraint. And he is very upset that lots of people ignore it. So, and
17 kilometers.
17. So that, yeah, that's this one here, that photospheric radius.
Yes.
So this here is just the uncertainty because we don't know the mass. So, but if that is the photospheric radius, then somewhere here that object has to live. So, which indicates
mass is not known?
No. You just know the radius, yeah. So you have black body spectrum, you know the distance, you know the luminosity. With that you can calculate the mass. So actually, so if you neglect this one now, for now, we are in a very convenient situation. So there is a small window only for equations of state. There's not much room left. Excellent. So I think we are really we had good progress over the last 10 years or so. This is completely a very convincing and promising result.
If you already told us, please excuse me. So can you explain this line which is called limit?
Yeah, basically that's, you have that redshift, yeah? Redshift, 1 minus 2g m over r appears there. So if that happens, if the mass, so basically if 2 times the mass is equal to the radius, then the whole thing becomes a black hole. And that's what happens here.
So that is just a formation of the horizon.
It's exactly that relation. So 2gm is equal to radius. Yeah, exactly. It's a horizon. Actually, there are some refined versions of it which go a bit below it. But I think that could already be. So probably the actual causality limit, so in that horizon sense, would be a bit over it, but not much. So this is a serious constraint. So there's not much debate about it. Which is interesting too, because some people claim that there are 2.7 solar mass neutron stars, or 2.8. So that would mean that you have a complete new quality in the equation of state, because you have to reach that mass, and you see it's in that domain. So you would be close to that limit. The only way to avoid it is that you have a neutron star which is much larger. So you would have to shift all that stuff to the right, and none of the models so far can do that. So Latimer, for instance, is a great fan of that Black Widow object. So Black Widow was in the other talk, in that list of neutron star masses. And Black Widow is likely, or claimed to have a mass of 2.7, with large uncertainty, of course. But 2.7, really, it would be nice to have it, for two reasons. First of all, how to explain causality, and the other stuff is how to get that right with heavy ion collisions.
And what with the 17 kilometer, also a problem, because if I want to go up to 2.7...
No, that's perfect. So
yes.
yeah, that 17 you have to read like that. You have to be in that region.
Ah, okay.
So it's not excluded. It's that's what you want.
Oh, okay.
Hmm.
So did you also explain the Marquez equation why there is upper limit for radius, 17 kilometers?
Yeah, it's so what is measured is the distance of that object, and the surface temperature could be determined from the black body radiation of that object, and it's almost perfect black body.
Yes.
So if you have black body, you know the temperature.
Right.
And
So what if?
so if you know the luminosity and you know the surface temperature and the distance, you can calculate, because you have the luminosity, so you know how much light you get basically, and that allows you to calculate the surface of that object. And if you have the surface, you have the radius.
Is it just observational effect, or there is some theoretical reasoning why, and if it is more than 17 kilometers, then it's not anymore neutron star?
No. So opposite. So you need to have a radius. So if you take that one serious, so in neutron star physics you always have to be very careful. So I stopped being careful. Everybody knows now that I'm very careful about the constraints. So don't take anything for granted or so. So, but if you take it serious, you have to be in that gray shaded region with your equation of with your mass radius curve. So these here, they would be fine. They have a high mass. They are in that gray shaded region. That's all we need if there wouldn't be flow. That's why flow is so interesting.
But it's in the no curve fulfills all the criteria. Because either they break the trouble with flow, or the trouble with the radius, or the trouble with the mass.
Seems to be like that, yeah?
Yeah?
It's interesting, isn't it? Huh?
So no one does the job.
Exactly.
If
And
you take all the constraints seriously.
if you want to take it really seriously, yes, it is like that. And that was actually the result of that paper. I cited it here several times, Klähn et al. 2006, where we did exactly that analysis with lots of constraints. None of the equations of state fulfills all constraints we know. That means either the constraints are not really constraining, so some of them you can just forget. Question is which one, you don't know. And the other possibility is we have a serious problem with our equations of state. You can choose. So of course I think that not all observations are rock solid. So, but it's really a tough thing to sort them out. So that was nuclear matter only. Actually, I wanted to speak about quark matter. So what is the problem with quark matter, and why I did elaborate so much on the nuclear equation of state? That's because one of the big unknowns when describing quark matter and neutron stars is the nuclear equation of state already, because all what we do so far are effective models where we model in some quark. But if you have trouble already on the nuclear level, so in your understanding of nuclear matter, then basically you're screwed, and that's what we are. But still we can go on and try to unscrew us. So what you would like to have in the long term, of course, are nucleons described as quark correlations. So you want to describe confinement and deconfinement in a neutron star. And that's a tough exercise. In medium, nobody did it properly so far that you really get an equation of state. So in vacuum, it's attacked. So what you can do, for instance, is you can start describing mesons as bound states. You know that, beta-salpeter equations. Then you could do, for instance, so that's how people do it. You make that quark-diquark approximations that you say, okay, nucleon effectively can be a bound state of stuff like that. You can do it differently, of course. Some people solve really the three-particle equation, try to do that. But it's very advanced, and that's what's taking place in vacuum. So it's really not much done in medium. Rischke did something with Wang and Wang recently, a year ago or so. But I think not to the level that you really have an equation of state which you could plug into a neutron star calculation. So barely explored in medium, and that's a problem, which I won't solve today. So in medium, this is a challenge. We have to face it. We have to face it now, because if we don't face it now, okay, someone else has to do it in the future. But it's really interesting physics, I think. So the workaround you typically apply if you look into neutron stars is that you model a nuclear equation of state, a free quark matter equation of state. You do that independently. So both models have nothing to do with each other. And you construct a Maxwell phase transition or some more advanced kind of phase transition like Gibbs constructions, but I don't want to go into the details. Should I? Yeah. No, okay, that's a Maxwell construction, how I would do it. So it's just you have the pressure as a function of the chemical potential. So pressure corresponds to the thermodynamic potential. That's the negative value. That means if you have higher pressure, if you compare two phases, the higher pressure will be always favored, and that's how you construct a phase transition. So you take one equation of state and the other, and look at which chemical potentials they cross. And then you can plot, for instance, the density as a function of chemical potential, and then you would get that so the typical jump here, which just is a consequence of that you have different slopes in pressure. So density is derived as the derivative of the pressure with respect to the chemical potential. That's why this has to be not continuous. That's Maxwell construction, classical thing. And in the end, you will get an equation of state P over N where you have a jump like that. So the interesting question now, in particular, if you investigate the phase diagram, if it really is a first-order phase transition from nuclear to quark matter, is first of all, what is the density where it takes place? And second of all, and that's very important, how broad the transition region is. Because if it's a broad transition region, you have room for lots of instabilities in dynamical processes, for instance. So, and we don't know anything about it, so all we know is guesswork. So
it is symmetric nuclear matter?
This is actually quark matter, but it doesn't matter much. So this is really, so that's the student slide here, just to explain Maxwell transition. So it's nuclear. So this DBHF here is a nuclear model. So we favor this one a lot for reasons I will show later. And this here is an NGL quark matter model.
My question is whether it is symmetric nuclear matter.
I think it's quark matter, but really it doesn't. I will show real curves later. So this here was really for students to explain again shortly how to do a Maxwell construction. And to explain where that jump here in density comes from.
So mu is 138 MeV in this model now.
It's about
the critical chemical potential.
Yeah, yeah.
And the density in terms of nuclear density is also 3. The first onset of the mixed phase.
Yeah, it's roughly 2 times saturation.
2 times saturation.
So probably it's neutron star matter, because in neutron stars the transition happens quite early. So 2 times saturation density would be quite early for in symmetric matter. It's not completely unrealistic, but probably this is a quark matter equation of state. Neutron star equation of state.
And when you go to quark matter, when you increase because then there's load changes, yeah? There's local pressure.
Yeah. So that's the point. Ah, yeah. Here, that sentence is actually important. A phase transition softens the equation of state.
Why?
Because that's how you construct the phase transition. So you go from the favorable equation of state at higher pressure to an equation of state again with higher pressure. So that means the slope of the pressure increases. Then you can go through all the calculations, but what you get in the end is that you always need to have that less stiff behavior. You can translate it directly in terms of the gradient of the pressure, or here in the density. If you wouldn't have that, first of all, you wouldn't have a transition. Second of all, you would have a negative heat capacity, basically. So it has to be softer in the point of the transition. It doesn't mean that it can't become stiff later, again. But first it has to soften. There was a recent paper by Romachke where he, so he was quite brave. What he did was a phase transition like that, basically. And what it looked like was there was some nuclear matter equation of state, and he did his quark matter equation of state, which was a very nice idea. He did it from perturbation theory. So he, in principle, he extrapolated from high densities where we know the behavior of QCD, some more or less. And what he got was an equation of state which looked like this, basically. So that, of course, looks very... So the problem about what he did was that this region here was very narrow in chemical potential. So delta mu was really order of MeV, few MeV, which is a very small region. And his argumentation to have a... No, actually, it went different. It went like that. Oops. And what he did then was to say, okay, this is fine, we have a transition here. And later, you would have a second transition from quark matter back to nuclear matter. That, of course, you don't want to have, so he just basically neglected that part.
But why don't you want to have it? If it is favorable, if the pressure is maximum?
No, you want quark matter.
But why? I mean,
yeah,
you have to take what the pressure...
You have to take...
yeah?
Exactly my opinion. In particular, of course, you can say, okay, you have model inconsistencies here in the nuclear matter part. And you can say, for that reason, the high-density part is probably pointless. So I don't have to think about it anymore. The problem starts if you have a very small region, because now you say, okay, I accept it here, but I dismiss it here.
Right.
Which is principle, it's not much a difference. So, and that's where you can criticize him. What he got with that was an interesting thing. So he got an equation of state which effectively stiffened after phase transition, because this here corresponds to a stiffening of the equation of state. And if you have a stiffer equation of state, you get higher neutron star masses. So you got a completely different behavior what you would expect. So typically a phase transition in neutron stars, so if that is the pure neutron star equation of state, a phase transition usually looks like that. So either you get some unstable configuration, so it goes straight down, it branches off the quark matter part, or you get some softer, less massive branch, which would be stable. So what he got with that approach was very nice, because it would solve a lot of problems. If it would work like that, what he got was that he had a rather soft nuclear equation of state, and then his quark stars branched off to the top. So, but still the method is very doubtable, what he did. So it's almost cheating. I was a bit upset. Okay, this is for, yeah, that was the students part now. It's basically Wroclaw model. Do I have to go into that, or you all know it? So it's contact interaction between nucleons. You get self-energies, scalar, vector. So scalar renormalizes your mass, so or changes your mass. Chemical, so the vector part is important to change your, gives you an effective chemical potential. So you change your effective, and that's the important part. If you change your chemical potential density dependent, that means you change the stiffness of the equation of state.
Let's go.
Yeah, I think so too. And then we come straight to the next part. So if we have the nuclear matter equation of state, so now in Wroclaw or whatever model, so we are basically at that step, and now we want to come from this region here to that region. That means we have to look at these degrees of freedoms, which are quarks. So what is so special about quarks? Some statements I want to make. So we have two special things about quark matter which we have to take into account. One is confinement, so no isolated quark has ever been observed. Quarks are confined in baryons and mesons. The second property we have is the dynamical generation of mass, which at the current stage, so the focus is on if you deal with dense matter. So you really try hard to find chiral models and not just constant quark mass models. So, okay, the typical argumentations here. So proton has 940 MeV, constituent quark with each 5 MeV. Still, so that means that the 98.4% come from somewhere. You can look at the effective quark mass in a proton, which is 313 MeV, effective quark mass in a pion at 70 MeV. So that means something non-trivial happens in a pion and a proton. So it's not, of course it's the same mechanism, but mass is generated in a very different way for both of them.
Just a very, very small remark. It can be that actually this number goes to 95%. Because the sigma term, that is also a big discussion in the community,
Yeah.
chiral models. I mean, you can do it better there. So the mass which you have only from explicit symmetry breaking, I mean, what naively is 15 MeV,
Yeah.
it can be a bit bigger than around
I have-
15 MeV. But
I have no problem with that.
Side comment.
Okay. So, of course, meanwhile, we think to understand that quark masses are generated by interactions really out of nothing. So if you apply the proper models, you are able, even in a model in the chiral limit where you have no bare quark mass at all, to generate a big amount of mass. It's just through interactions in QCD through self-interacting gluons. And this is a distinct non-perturbative feature. That's important too. So if you try perturbation theory, you won't reach any mass at all. If you start in the chiral limit from 0 mass, you won't get mass. It won't happen. So that's what you need. So confinement and dynamic chiral symmetry breaking are probably connected. It's not trivially seen from the QCD Lagrangian. So if I make that statement here, I speak about most studies I've seen which try to be microscopical. So that would mean Dyson-Schwinger approach in medium. It would mean large NC expansion where you not have the infinite NC, but really finite NC. So then you see that even that quark-ionic phases we spoke about, that this upper limit where you have, so this large NC hyperon quark-ionic matter hypothesis was that you have confined but chiral symmetry, chiral symmetric, no, but massless basically, yeah, chiral symmetrically restored nucleons in that region. So, but this is really NC to infinity. If you take finite NC, what I've seen so far, it looks like it comes down, and this here goes up and up. So, and that chiral transition and the deconfinement transition are likely to be together. It's likely that this is a connected first order phase transition. No guarantee though, it could be different. So, of course, these are very fundamental questions, and I'm not a very fundamental guy. I'm more the guy who's interested in neutron stars, so I look into what is available. Of course, it would be nice to have it all together, but reality is, what do we use? We use back models, and I don't mean any fancy back models. So what we use is really a thermodynamic back model. It means you have an ideal gas, you subtract your back constant, and say that's confinement, or the relic of confinement. It's gluon condensate constant, or something like that, where it comes from. So certainly they account for confinement somehow, because they're constructed to do exactly that, but they don't have any dynamic chiral symmetry breaking. Quark masses are fixed, and they are not fixed to the asymptotic bare masses, but really to some finite numbers, so which are not well justified, at least not over the whole phase space. NGL model, we are in a similar situation, even it looks a bit better. NGL models typically account for chiral symmetry breaking. That's exactly why we use them, because that's a strong feature we want to have. But they don't exhibit in a trivial way confinement. So they don't have it as far as I see. So some people claim that if you really would take into account bound states, you could have something like confinement. So yesterday we spoke about that. What I think what you have to show in the long term is that if you apply a model like that, what you really want to see is if you construct baryons in such a model and you claim its confinement, the least thing I, from a naive point of view, would expect is that your free quark density goes to 0. Because that's what confinement would be in the most naive, but the observational sense. We don't observe free quarks, so you would have to get that out of the model. And I haven't seen that. So a colleague of mine is doing stuff like that. So he's calculating mesons, baryons, and so on in vacuum. And he does finite temperature expansions, and there some density pops up. It just comes out, so he doesn't get rid of it. So it's not what I would understand to be confinement. But that problem isn't solved by anybody, so it just maybe a point for discussion or even for suggestions. That would be.
So the raw meson decays into quark anti-quark
Yeah.
And also in the PI in general.
Yeah.
Where confinement is in some thermodynamical sense to be understood.
Yeah.
But notice you have decay to quark and quark.
Yeah. Yeah, that's okay. Yeah, you can do that, but so
It's a problem, so to say.
yeah, I need thermodynamics, and I don't want to have free quarks in a confined phase, so they don't belong there. So yeah, lattice QCD, of course, is ab initio, but so there's my problem again as a neutron star guy. So T equals 0, finite mu, that's definitely not the domain of QCD, lattice QCD. Perturbative QCD doesn't work as well because it's perturbative, so I don't get simple features which I want to. So the approach which I think is fruitful for the future is really the Dyson-Schwinger approach. So basic idea is you derive gap equations from the QCD action. Of course, you get that infinite tower of coupled Green's functions, so 2-point function coupled to 4-point, 4-point to 6-point, and so on and so on. You have to make your truncation and so on, but what you can try to preserve certain features of QCD, so you apply Takahashi identities and all that dirty business, which looks very complicated to me as well. And what you get in the end is a self-consistent equation where you calculate self-energies which depend on the propagator here of the quark and of the gluon, of course. You have some quark-gluon vertex. And this has been applied very successfully in vacuum to describe meson and hadron properties. So there are several groups doing that. Alcover is doing it, Fisher is doing it since a couple of years. Craig Roberts, where I've been a postdoc, is doing it with steadily increasing excitement. And but what's missing, of course, is still an equation of state, which would have been derived in that framework.
So what is the problem in getting equation?
It's complicated. It's complicated. So there are two problems actually. It's really so. I'm very sure and very convinced there are many fundamental problems to solve it, but not thinking about the fundamental problems. It's difficult already in vacuum to calculate, in particular, bound states and stuff like that. So it takes a good amount of computational time. You have to be very precise because you have that so you have to regularize your theory and so on. So there are lots of things. The next point is people who do Dyson-Schwinger, who would be able to do it, they are so excited about vacuum because now they really start to calculate all that interesting properties, form factors, mass spectra, and so on. So they have lots of stuff to do. And they say, why should we make it more complicated? We are happy we have it under control. So they don't want to help me.
Aren't they saying that in this approach there's no problem of cosmological constant? I mean, because all the condensates that you're talking about is not the vacuum condensate, but it's
yes, that's what.
Yes.
Yes, Stan Brodsky and Craig Roberts made that statement. So they say that the condensate you have is really. It doesn't make sense to speak about a condensate in a medium in vacuum because what should condense around what? So what you need in order to have a condensate is really some core for that. So which you have in bound state. So all the condensate you have really is there. So and vacuum is a proper vacuum in that sense. So you don't have that background condensate.
But it's exactly that the vacuum has a condensate, so it should be everywhere.
No, exactly not.
That's the other way.
Well, this is what Brodsky said in his paper, but the question if it is correct.
Oh yeah.
Yeah, of course.
I guess the question is whether well, I mean, obviously it's not generally agreed on. A lot of people are objecting.
Yeah, sure.
However, I think there is also Ken Wilson's collaborator in Holland, I forget his name, Glass, I think, who worked on the renormalization group approach, and he's also agreeing with the Brodsky's idea by looking at the renormalization group argument. That development is something like that is happening. So there's a minority of people who are getting that kind of description.
Yeah. So one point they have is that they say if you have condensates really in vacuum everywhere, you define something like an ether. So it's a concept which we actually wanted to get rid of. So in that sense, I understand that this idea is very appealing.
But who cares about the cosmological count? I mean, we have.
Oh, cosmologists.
Anyway, it is off anyhow. It is wrong anyhow. with or without the contribution of the QCD vacuum.
QCD vacuum gives you just a small amount, but
Exactly,
yeah.
it is.
But what they're saying is that you essentially resolve the cosmological constant problem. I mean, in field theory, you have a vacuum contribution, which is huge. So they claim that problem, because the problem is that the infinite frame in that framework, the vacuum is trivial. So therefore,
So the condensate would be 0.
yeah,
But then
the
if I take
vacuum
an
is
hadron,
trivial. It's all in the hadron wave function, which contains all the. The matter wave function, which contains the content.
but the other view was that inside the hadron they have a high density and inside the trivial vacuum.
This is
So-
what we.
Features I want, this is the approach who provides most of them.
Yeah, but isn't this? Technically, isn't this very limited? They usually use the ladder approximation.
Yeah, ladder rainbow.
Yes.
Yeah.
That's very.
Yeah, but you have to look at what they get, and they get a lot. And so, see, the point is,
No, that is the question actually. If they can, if they are satisfied with the ladder approximation and so on, then what is the difficulty in getting within that approximation of the equation of the state?
okay, NGL model I don't have to explain. I will come to that, that's why I was looking for. So, okay, what we applied here was an NGL model. Basically the same as Valechka model, just for quark matter degrees of freedom. So the techniques are pretty much the same. So the only difference we had here was that there's a dike-quark interaction term. So we introduced Nambu-Gorko-Spino, so the usual business in order to get dike-quarks described properly. As it turns out, dike-quarks are important if you want to fiddle around with the equation of state. So if you want to adjust it so that you get along with the constraints. Without dike-quarks, it doesn't work.
So is it NJ model?
Yeah, this is here the interaction part of the Lagrangian for NGL model, as I use it in the following.
2, 5, 7. These are the good dike-quarks, yes?
Yeah. Exactly. So if you have such a model, you can start playing. So you can construct your phase transition, and the best way to see that it's really typical Maxwell phase transition is here. So you have the typical jump in density. And what we did we took the DBHF model, which has trouble with flow, which I indicated somewhere here as well. So, and we tried to fix it with a quark matter equation of state, because if it's too stiff here, and we know, okay, phase transition softens the equation of states, and you can say, okay, why not via quark matter? That's exactly what we did. So we looked with our, within the parameter range, what is possible, and it's well possible really to fit exactly that upper limit, which is of course nice because it gives you heavy configurations, and this is what you get in the end. So this here would be RxJ, which has problem. This would be DBHF pure, which has problems with flow somewhere in that region here. And this now is the hybrid equation of state, and suddenly everything works. So you have no problem with flow because it's constructed like that. So you see flow corresponds to the region here already. We come up to masses and radii, which fulfill this constraint, and we get the maximum mass as well. So that guy here, that's the onset of strange matter, so of CFL, dike-quark condensation, so color flavor locked phase. So this is rendered unstable. And that seems to be a general feature. You can avoid it if you introduce Polyakov loop and stuff like that. You can get stable strange a stable strange matter branch or twins or so, but actually I don't think at that high masses. So it seems to be a general, quite general feature of NGL models that you get neutron star configurations, hybrid neutron star configurations with stable 2 flavor matter only. But I don't want to generalize it, so there might be other parameterizations which get it for 3 flavors as well. So that's a nice thing. Doesn't look very systematic, so we did it more systematic. So here we really just varied the vector coupling and the dike-quark coupling. So what the vector coupling basically does is to stiffen the equation of state, while the dike-quark coupling moves the equation of state a bit up and down. So, and that's why it adjusts the onset of the transition. So there's lots of stuff to see here. It's a very, very heavy plot, but I will go through it briefly. So this region here, for that parameter choices, you don't have stable hybrids at all. So quark matter would be rendered unstable straight in a neutron star. This here is the opposite region. I call it quark stars. Actually, I shouldn't, because it just said that NGL model probably is not the proper thing to do in that region, because you have a phase transition really at very small densities already. So it's below saturation density. So what you would describe here would be a pure quark star configuration, which I wouldn't dare to touch with an NGL model. So, and in between that region here, that big white region, that would give access to neutron stars which have a quark matter core. However, this curve here corresponds to neutron star configuration where the maximum mass corresponds to that 2 solar mass object. So the maximum mass increases in that direction, so you would have that almost almond-like shape, which gives you parameters which are in agreement with that high mass constraint. Okay, that looks almost like a straight line. The massive quark cores you would find in that domain, and that actually is a quite promising result, because if you do the Fields transformation, by the standard Fields transformation argumentation, you would expect here a value of 0.5 for the vector coupling. Unfortunately, you would expect a value of 1 for the diquark coupling, so that would leave you somewhere here, which means you can't expect, if you take the strong, or the strict Fields values for the couplings, that you would have a stable hybrid core configuration. However, you don't need that necessarily. So that one, because you don't know what effects you forgot. So you can play a bit with that, and actually this is a change of 10%, which would really make a difference. Down in that region you would have hybrids too, but the quark matter core would be very small. So you would have a very small core and then it just blows up. So the interesting thing is that you can look at the same time which transition density you would predict in symmetric matter, so for heavy ion collisions. And that's interesting because the transition density is at that green line here. That follows pretty much the line of that pulsar. And it's a constant value, it's 4 times saturation density. That's what that model predicts. Actually, it's a bit high because we chose here a slightly different scalar coupling than in the other model. But that would be a longer discussion. So what do you learn from that? If you could prove that there is quark matter in that pulsar, that would mean that the transition has to happen at roughly 4 times saturation densities, maybe a bit beyond that. This is wrong here. If it doesn't happen, and that's the interesting point too, if you can prove that there isn't any transition like that in that pulsar, you know that the transition has to happen beyond 4 times saturation density. So because the transition density increases in that direction. It would be a very nice statement to have, because that would really give some guidance to experiments, to what densities I really have to excite in order to find some indication of the phase transition. Another point which I didn't mention before, but I should. If you look at this, the transition density here is very small. It almost looks like crossover, so that might be interesting too in symmetric matter. So you don't have to count on that you will have a large instability region, and lots of calculations I've seen really take that argument. They say, okay, there might be a large transition region. So it's really an important question whether we find somehow, however, I don't know, quark matter in a neutron star. Because if we find it, that would really imply that the transition region probably is small. And the reason is at high neutron star mass. So the quark matter equation of state can't be endlessly soft. It doesn't work, because then you don't get that mass. So it has to be almost a nuclear equation of state from the stiffness point of view. And that implies a small transition region. So on the other side, if heavy ion collisions now tell us that there is a large transition region, that would almost at the very same moment resolves that conflict here. So we would know that there's no quark matter in neutron stars. So in both sides there would be interesting statements to make if you make the proper interpretation. Okay, so that was the monster plot. And yeah, I want to come back to that quark matter medium stuff, because before that was a standard model. So NGL, everybody does, even on a better level than I've shown here. So that Polyakov extensions, and you can take other things into account. But I want to come back to that here, because I think it's promising, and we did some stuff on that. So what made me sad when I've seen it the first time, that was the momentum dependence of the mass gap as you would get it from lattice results. So these would be these results, these data points. And you get the same in Dyson-Schwinger calculations. So there's a distinct momentum dependence basically of every gap. So it's not only the mass gap, but you have the corresponding gaps corresponding to the Dirac character of your free propagator. So whatever you have there, you will have in form of a gap. So this is something you won't have not in a trivial back model. You don't have it in the NGL model. The NGL model gives you a constant density in momentum space. It changes with chemical potential only, but it's constant here in momentum space. So we can't have that. That means we lose all effects of that momentum dependence. We can't have it. Which probably is one reason why NGL won't have confinement in it, because confinement really is triggered by the behavior here in that domain a lot, how it works. So question is obvious, how does momentum dependence affect the gap solutions? What does the equation of state in deconfined quark matter look like with that? So yeah, and these would be longer term questions. So actually really it's not so difficult to take medium into account. All that happens is that you have the time lag component of the propagator. So if you just take the quark part of the equation of state and you get here the chemical potential which revokes Poincare covariance, okay, that you can deal with somehow, technically at least. And the same you have to do in the self-energy, of course. So that you're losing Poincare covariance basically means that you don't have two gap solutions as you would have it typically in the vacuum, but you get three. So one for the space-like, one for the time-like. And on top of that, these gaps become complex quantities, which they haven't been before. And of course, it depends on chemical potential and temperature. So you see that the parameter space is popping up quite fast. So it's not just that you have to take into account chemical potential, but you have to solve three gap equations instead of two. You have to solve them in 2 dimensions instead of 1. And you have to scan that parameter space of temperature and chemical potential. So maybe that's an answer why people don't do it. So it really increases the complexity of the actual technical problem. Straight, and a lot. So another thing you have to mention about that one, so typically you have two solutions here. One is the confined solution, one is the deconfined solution. So there's a Nambu-Gorkov phase, which is massive, and you have a Wigner phase, which doesn't have mass generation in it, not in a trivial way. So in the chiral limit there's no mass at all, then you can say just that the mass gap is 0. Still you would have these gaps. So in that sense, my question, the initial question, how does the momentum dependence of the gaps look in medium, is still there.
Why you have the complex gap?
Which one?
Number 2.
Why
extra complex value? Is it because the chemical potential is the
yeah.
Then why you
So
use the Euclidean?
I could go back to Minkowski, but then I would have complex gaps because this one is complex. So I can shift that problem from one side to the other. But that's the way you do it. But, don't ask me about the very deep details about it. So this is what you get if you write chemical potentials into an Euclidean Lagrangian.
So what are you going to say about the complex?
I don't say anything about that yet. So I've calculated stuff like that, but so what I want to make now is another. So when I spoke about cooling to be an important property of neutron stars, which you have to understand. So that means you have to understand transport properties in nuclear matter, in quark matter as well. So in both, of course. And so what I want to argument now in the following is really that maybe nature looks a bit more different than we would expect from a simple NGL and back model. And I make some very simple model studies here and want to speak about that. So what people do in vacuum is they have their self-energy. So here you have the gluon propagator. Here they make an assumption that they say, okay, there's an effective coupling here, and the propagator essentially is a free gluon propagator. So yeah, that would be that rainbow approximation, basically. So this here is the quark propagator, and the quark gluon vertex you replace just by the unrest vertex. And so this here would be the typical choice of Craig Roberts, for instance, to describe his vacuum properties, and somehow you want to put that into medium. You would have to do the same stuff, basically, as before, really just with that little change. Still, that's very complicated. We try to do it a bit, but actually, so this one here, we neglected. I looked into that term. A Chinese collaborator looked into that term. And the result of that have been two publications. So that first term is known, actually. So it has been investigated in vacuum. And the nice thing about this one is if you take it, you can calculate, you can evaluate the model analytically. It's very nice, very neat. You get straight solutions, and you can claim that it's a confining and the deconfining phase by some argumentation.
Is it calculated though? The second one?
This one?
Second one.
This one?
Yeah.
No, this one you have to do numerically. Or what do you mean?
No, I mean, how did you come about this exponential of the...
As I understand it, so this form has developed over a couple of years in order to describe the meson properties in particular. It's an ansatz, yeah.
They start from that,
Yeah.
and then they feed the parameters to get the meson masses.
Yeah. Yeah, that's what they do. So, and it's as far as I see it, quite successful. So they get the meson spectra right, they can calculate form factors.
So here, D is what, constant?
Yeah, these are constants. This is a constant, this omega is a constant. Yeah, and that's it.
So G is, what is G?
This here?
Oh, okay, there.
Yeah. So you make this transition here. So there's coupling strengths, but you are just.
What's the meaning of a G? What's the meaning of a G?
Of this one or of this one?
Yeah, that one.
Large G? Yeah. So the idea is you don't. So there's a nice discussion going on for years. Meanwhile, I think between Alcover group and Roberts group, what to do with this? What to do with this guy here, with the gluon propagator? So. Alford claims that the infrared behavior is, not Alford, Alcover claims that the infrared behavior of the gluon propagator is extremely important. Robert says if I look into the very infrared behavior, that means I look at distances of kilometers between quark, and I can't believe it's important. So he just says, okay, we make our ansatz and that's it, while Alcover and Fischer and so on, they really try to solve gap equations for the gluon propagator as well. So I think both have a point, and it's interesting to see how that will end. I think if there is...
So that G effectively includes the...
So that G here is a fake solution for the gap equations for this D, for the actual D. So here you have just the free part, and this here is the modification of all that stuff which we don't know. So that's the ansatz for how this one should look like, basically. Not really.
So in the limit when this G is equal 1, the propagator of the gluon goes back to his perturbative form, right?
Yeah. Yeah, that would be certainly true.
So in which limit this stuff is going to 1, that would be really good to understand. It doesn't seem
so this term here, this is important for the UV domain. So that's what you want to have in order to reproduce the running coupling of the... Yeah, and this here basically that's really the confining nature of the gluon you want to simulate, which is triggered by the infrared behavior of the gluon propagator. So much is agreed on. There are plenty of reviews on the topic. I would like to go on to that very simple results. So, as I said, first time you can evaluate analytically. It's obvious, it's a delta function, so that should make things easy. The nice thing is, if you go into medium, you can go analytically. You can go on analytically quite far. For instance, you can calculate the one particle density distribution function, and that's what I did. The second term you can evaluate as well. Unfortunately, not analytically, so you have to do it numerically. So we did that together with Huan Chen, who recently calculated even some neutron star configurations with it, which would be worth another remark, but I don't make it. The interesting thing is that you would obtain an NGL model from expressions like that if you have a delta function in configuration space instead of the momentum space, so it looks like that Munchik-Nemirovsky model is the evil twin of the NGL model. So it's really contact interaction once in the configuration space, once in the momentum space. And that's the difference between it. So if you evaluate that, and that's what I did, I just want to show the results, you get the distribution functions which at 0 temperature in the classical cases, so NGL model, Beck model, and so on, are just step functions, where the step is determined by the chemical potential. That behavior changes now. And that's interesting. So you have a domain here which is defined basically by the coupling constant and the chemical potential. So here's chemical potential, this is square root of that term, and you have that gap. So the nice thing about that, of course, the coupling here, it's a finite number. That means if the chemical potential goes to very large values, this gap will become smaller and smaller. So if you do that, so if you increase the chemical potential a lot, you will finally get that step function behavior. So here I have normalized it to the chemical potential to make that point clear. So asymptotically, we have a free Fermi gas in that model. So bad news, in particular from that model or for that model, probably both is true, is that this happens only at very large chemical potential. So you can look here at 0.4, which is already quite decent chemical potential. So this is what would be realized in a neutron star. Maybe it would go up to this one. You don't have Fermi function behavior at all. That means all approximations which make use of the typical Fermi surface arguments that you say, okay, you can occupy or take from states only from the surface, Fermi surface would break down if this is true. But of course it's not. I mean, it's a simple model. If you look into that other evaluation, so if you, okay. So you can go on from there and see what the equation of state looks like, because that's how I started, why I did it. So these terms I got analytically. The next one I would have to integrate. So I take this distribution function, then you do the standard thing. You integrate over the Fermi function, and you get the you get the density as a function of the chemical potential. And in the next step, you can integrate over the density over the chemical potential, and you get the pressure. And that's the equation of state. So that's pressure as a function of density. So since we have the peculiar behavior, it's not only that the Fermi sphere is growing with increasing density, but it's getting more dense. So that means you have an additional dimension in the problem regarding the chemical potential. So it's not with mu to the 4, but with mu to the 5, just to the increase of density. And that's what you see here. So that actually free Fermi gas, so what Beck model would do, or NGL model as well, you get only at very large chemical potential. So interestingly, this doesn't depend, if you scale it probably, on the actual size of the coupling also. So it's a scale invariant result, which somehow looks nice too. And so a coupling we chose here in order to describe meson properties was 1 GeV. If you take 1 GeV, you would see that, okay, free Fermi gas behavior maybe starting from 2 GeV if you look, and it's generous. So it's a completely different behavior than you would expect. So that is interesting.
How does the, I mean, you know, how does this asymptotic density regime that you're talking about, how does it jive with the statement that the asymptotic density, large density, color flavor locked state should
It goes, I can't make any statement about that since I didn't consider.
Yeah, I mean, that's
Yeah.
QCD.
Yeah.
QCD says.
Yeah. I don't get it out of here. So it's a simplistic model.
By the way, can you identify why there is a mu to the 5th power region is there?
That's what I explained before. So usually, the distribution function is just a step function. So you integrate that over momentum space. That would give you the regular, in a regular sense, for the density, a mu to the 3rd behavior. Yeah, you have p squared dp up to mu. That's mu to the 3rd. But I don't have a step function. I have a thing which is growing with density too. So this behavior here, for instance, at 0 momentum, this grows linearly at small chemical potential with mu. So it's not step functions times p squared p dp, but it's something like p times p squared dp. And that gives p to the 5th, p to the 4th here, or mu to the 4th here. And in the pressure, you integrate again over density, because that's the thermodynamic relation that holds.
Oh, okay.
And
so
you
I
get
just want to
mu to the
think
5th.
P to mu to the 4th
Yeah.
versus mu to the 5th.
Yeah, so density with mu to the fourth instead of mu to the third, and pressure with mu to the fifth instead of mu to the third, mu to the fourth.
I'm sorry. I mean, if QCT says at the asymptotic density, we should have a color flame locked phase, in which case there is no free quarks. There are no free quarks. I mean, they are all bound.
Yeah, but in order to describe a color flavor, in order to describe a color flavor locked phase, I should allow my model to describe color flavor locked.
No, I understand that within this picture. Well, then I would say this model is not consistent with QCD. This is what I'm saying.
Yeah, of course not. Yeah, so I don't say that I solve QCD here. I say I'm solving a model which has features of the Dyson-Schwinger approach, which claims to be close to QCD, which even that statement is doubted by lots of people.
Okay,
so I try to.
You agree with my?
I try to be very careful here about what I'm saying, and if you think about what is done back models, okay, so you have you see it. Nah, no, actually you don't have the corrections as well, yeah. And
well, if that is the case, then why would we be using this model to describe asymptotically large densities?
I'm not so much after the thermodynamic behavior at ultra high density. What I want.
Where the neutron star is that what you're saying?
That's one thing I say, and the other thing I say is that this might be extremely important for if you really want to calculate transport properties of a system. So if your distribution functions of the particle are not not classical step functions anymore, lots of approximations are previously done just break down. They don't work. So that's a very simple model. So a reason, or you will see that actually this is a very peculiar model if you compare to what you get if you take that other effective gluon propagator. There you get a distribution function which looks completely different. So instead of that, what we had before, where it goes down here near the Fermi surface, now you have a decrease here in the distribution number. So for small momenta, it's completely the opposite behavior. But still something happens at low momenta. And all the statement I want to make is QCD might be surprising, even in that domain where we just say, okay, it's deconfined quark matter. What exciting things can happen there? So it will shift a bit from here to there, and maybe it's stiffer or not. I think it's a very promising field to go on. In particular, if you look into cooling processes and so on of quark matter. So lots of stuff might be happening here. For instance, superconducting phases. Yeah. So what happens to a superconductor if that Fermi surface argument doesn't hold? I don't know. Same for basically even that condensed phases, color flavor locked or not, it could look different. And that's all I want to say. So the world could look different than we think it might look like. And that's the end of what I was speaking about. So conclusions, that all we had. So still best candidate I see to make real progress on the field of deconfined quark matter, not confined quark matter, on deconfined quark matter, which is barely understood, is the Dyson-Schwinger approach. It's non-perturbative. It has, so we can compare to the confined domain, because there are calculations done. It has all that nice features we want, dynamical chiral symmetry breaking. It's applicable at finite mu, at least technically, and there are extensive studies at t and mu0, but still, and that's what I see too, there's lots of work to be done before this will nearly or fully work.
So what about the problem of the complex chemical potential? So what you do is after you finish the calculation, you use the rotation back to the real, or what do you do?
No, you just instead, so technically it just means that instead of 2 gap equations which you had before, now you have 6. So 3 times 2. And that's all. So they decouple, but they are coupled. So the imaginary part of the gap function now is a function of the real and imaginary parts of all other gap functions. So it's just an increased complexity. But it's not a fundamental problem that they become complex. It just makes it more complex. It's just a technical issue. It's not a fundamental problem also that they become complex valued. Not at all. So if you calculate observables, for instance, so that imaginary parts of the gap functions are typically odd functions, so not even functions. That means if you calculate observables, you won't notice that there is a complex contribution to the gaps.
So what's the meaning of the imaginary part of gap?
In the classical sense, probably you would understand it as some kind of damping or introduced time scale or lifespan or whatever, but I would be careful about that too. If you look, for instance, into, I mean, if you look into propagator, yeah, so propagators in many particle physics often have complex valued self-energies, and this is what the gaps are. They are, in some sense, self-energies. So, and then you typically would have, I mean, as you typically have it, so that would be the imaginary part, and you would have a real part which goes somehow like that. So that you connect to lifespan, and this you use to identify poles or whatever, which might be important, some bound states. Or
No, if you are talking about the, let's say, spectral function,
yeah,
no problem at all.
yeah. No, so this will be modifications.
But if you are talking about the gap equation,
Yeah.
gap is not an, I guess, position of a pole and so on, right?
Hmm?
Gap is
Yeah.
not a position of a pole.
Yeah, but that's how in medium, so how statistical physics works in medium. So you shift your pole by chemical potentials in Euclidean medium. So you shift into the complex plane. So that's not a problem. You do that.
Oh, do you mean that this is a kind of some quasi-normal mode? Oh, so this is, what do you mean by gap is nothing but just one, I mean, the complexified spectrum? Is that what you're saying?
Self-energy, yeah. So it's an effect of that.
Uh-huh.
Sure it is. I mean, if you, that's how you,
But what I was asking is that...
yeah, if you look into the general solutions, of course, you can write that as one time, no, so just add a 1 and subtract a 1.
Let me ask you just one question. So this appearance of a complex pole is not just only in Euclidean formalism, even in the case of the you performed calculation in, I mean, the
In-
Minkowski.
Yeah, you have,
Still get the,
yeah, you always have it.
Oh, that was the question.
Yeah. No, yeah, you can't avoid it. So the only thing you can choose is which you put into the complex domain, as to speak. So so either the chemical potential or P4.
So that means that even after you
Or the energy.
calculate, you and Euclidean, you relocate the chemical potential, and then you still get the complex pole.
Yeah.
And that complex pole should be the something real dynamic. Okay. And now use, I don't know what's this. Complex gap.
I mean, you have that already. To some extent, you have it already without a self-energy, without any gap, yeah? So you have here that complex contribution to P4. So that shift of the chemical potential. And now that shift, and maybe you can understand it like that, that shift is of course modified too by solving the gap equation. So you have to, actually, you need to have a modification in both domains, on the real and in the imaginary axis.
So can you interpret this complex imaginary part of the presence of the imaginary part of the gap as instability of the vacuum described by this gap?
The instability of the vacuum.
You know that if the gap means, right, that the certain kind of excitation below this gap is forbidden. That is kind of meaning of a gap, and that is guaranteeing the stability of the properties of a new vacuum.
Mm-hmm.
So now, if you claim that there is a complex part for this gap, so I'm now having some. I need some new idea how to interpret this complex gap. If you are
So you,
put it like that,
Yeah.
indicated there, which is kind of decay width
yeah.
of this, then it means that this kind of gap is transient, and it just this new vacuum is just decaying away soon. If I'm wrong, then I need some new idea. So.
Yeah, it's very hard for me to make a qualified statement on that. So to give you a decisive answer.
Which Lagrangian you are solving with in terms of Schilling diagram? QCD.
Supposedly it's the QCD Lagrangian, and in fact, of course, it's not, because you make the truncations, and if you translate that into a Lagrangian again, yeah, but you start.
I don't care.
Yeah, but you start from QCD.
QCD.
Plus these answers of the gluon propagator.
No, that comes later.
That comes later.
Yeah, so Dyson-Schwinger equations you derive strictly from the QCD Lagrangian, but it's not written here.
So this chemical potential is a chemical potential of quarks or baryons?
Quarks. It's quark chemical potential.
So you are
So-
describing quark chemicals.
Yeah. So no mesons here, no baryons. I don't try to confine anything. I just look at the deconfined solution, even though there is that massive solution which supposedly is confined. But of course, how you speak about quark confinement if you don't have any baryons? So it's a point which is not very sensitive to do.
So do you have any the description for the dispersion relation for this quark after you calculate this self-energy?
I could look for it. For that, I would have to go to no. So
I'm very curious about
the complex momenta. No, I didn't do it.
if you solve the Schilling Dyson and if you can send me the result about the consequence of this dispersion relation. I mean the full propagator by adding this the self-energy you calculate.
Yeah, I mean the propagator is given really here by Munchik-Nemirovsky. That's in vacuum, and the vacuum extension is very easy. So you really have analytic expressions for that A and B gap.
This is too complicated for me, so I need some kind
No,
of...
mine, it's just mine which looks complicated. These forms are very easy actually. So yeah, so the propagators are so easy that I did not even write them down. It's something like 1 plus p squared over something or so. I don't recall it perfectly, but it's a very
Some analytic expression.
yeah, that's a nice thing about it.
Which paper is that? The Chen or?
Munchik-Nemirovsky.
Oh,
Munchik-Nemirovsky 83, that's the vacuum solution. Klähn et al. 2010, that's the in medium part.
Why don't you start directly from the Minkowski formulation of the propagators? Then you have P plus mu. You don't have
It doesn't change anything.
Right. But
So so I want to stick as close as possible to Dyson-Schwinger because I want
this is why you wanna have
I want to travel-
Euclidean solution.
I want to travel on their backs. That's my plan. So I let them do all the hard work in vacuum, and I see what happens in medium. So
Are there some lattice work with purely imaginary chemical potential? Yes.
yeah, there are some approaches.
Because you could compare, because in that case mu is imaginary and then it is real there, it should simplify everything.
Yeah, but again, if you look into observables, it shouldn't change much, or should it?
No, it makes everything easy. I mean, in lattice QCD you don't have the same problem.
So you mean just modify that P4 by, no, not by I mu, but just by mu?
Yeah, if mu is a purely imaginary number, and there are some lattice toy calculations, because of course you don't have the same problem in lattice if you do that.
Yeah, well,
In order to face nature, you have to continue back because
Right.
that's not defined. I mean, you cannot do that.
It is, but
There's
just
no
to
way.
compare them, I mean,
For small value of mu, you can.
for instance, yes.
You don't-
So qualitatively, what is the difference between this paper and your result?
between Munchik-Nemirovsky? Munchik-Nemirovsky didn't account for chemical potential, so they stopped in vacuum. So I was surprised actually that I could solve that next case analytically so far, because it didn't look like that in the beginning, but then
I see, they didn't do chemical.
they didn't do chemical potential, no.
So you did find the chemical potential version of this.
Exactly.
But I really need the result in the presence of a chemical potential.
It looks very much the same, so you will find the expressions here, but so if you're not satisfied with what you find, of course we can talk about it.
Because what I have done recently is doing the same thing in terms of holographic procedure. So I need to find some reference to compare.
Very good. I mean, don't be disappointed. It is a very simple model, so I don't claim that this is connected to anything in the real world. But I think the features are interesting enough of both of these cases, and there is no reason to believe that if you take that guy into account, which finally makes this work in vacuum, that you would get suddenly proper nice Fermi function behavior as you are used to. So that's the whole point of that story here, to make you aware and sensitive of that there might be trouble hidden.
When you go from the first to the second term, this has been done, yeah? You did the first.
I did the first, and Juan did the second.
Does it change much when you include the second term?
Yeah, I showed you. So
this was exactly from this part to the.
from this to this. It's a lot. It's complete different behavior. Which is interesting too, because actually the second term. So the first term is a delta function. The second one is something like delta function too. Yeah, so it's very close to that. So it doesn't look so different. Usually you wouldn't expect that it causes so much differences. Yeah, but okay, the k-squared behavior is a bit different. So no, okay, it's not exactly the same, but still I found it surprising too. That's completely different.
It's also, you say, a small k contribution.
Yeah, yeah.
Exactly as the delta.
Yeah, yeah, exactly. So the interesting thing too is that the way we did it was the opposite. Yeah. So first he solved that one. I solved it too actually, but I wasn't happy with the numerics, so I was looking for a test case. So I didn't believe Juan, because my results looked a bit different, and then I started to do analytic stuff in order to check the numerics. That was the plan in the beginning, and then I found out that this model is so nice and handleable, and actually I'm quite happy that I have done it, because the differences are very distinct.